Energy is not made of anything. It has no mass, no volume, no substance you could ever hold in your hand or weigh on a scale, and yet every atom in your body, every photon streaming from the sun, every thought firing through your neurons right now is built from it. Energy is the only currency the universe accepts, and no one can tell you what it actually is. For more than 200 years, physicists treated energy like water. Smooth, continuous, infinitely divisible. You could have a little or a lot, and there was no smallest unit, no bottom to the measurement. It flowed, it transferred, it made sense. And then, in the year 1900, a German physicist named Max Planck discovered something that should not have been true. Energy does not flow, it jumps. It comes in packets so small that 10 to the 34th of them fit inside a single joule, Quanta. Indivisible chunks of reality that arrive in fixed amounts, like nature had been using quantum money this whole time and no one bothered to check the denomination. That discovery cracked the door open. What came next tore the hinges off. Light is not a wave, it is also a particle, a photon. A packet of pure energy with zero mass that somehow travels at 186,000 miles per second. Space is not empty. It is an invisible ocean, a quantum field humming with 10 to the 19th vibrations every single second, particles popping in and out of existence in a foam so fine we cannot see it, only measure its effects. And the deeper we look, the quieter it gets. The less energy resembles a thing, and the more it resembles the thing that things are made from. This is not philosophy, this is physics, and it dissolves everything you thought was solid. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Energy was a story we told ourselves. A useful story, an elegant story, a story that for more than 2 centuries seemed to explain everything about the way the world worked. It let us build steam engines and predict the motion of planets. It gave us laws we could carve into marble. And then, quietly, in a series of experiments conducted in dark rooms with glowing metal and precise thermometers, the story fell apart. Before we talk about what energy actually is, we need to talk about what we thought it was, because the picture we carried in our heads for generations, the one that still lives in high school textbooks and introductory physics courses, is not wrong exactly. It is incomplete in a way that changes everything. The classical world, the world of Isaac Newton and James Joule, and all the brilliant minds who built the foundations of modern physics, treated energy as something you could pour, like water in a pipe, like wine in a glass. You could measure it, you could transfer it from one place to another, you could store it, release it, convert it from one form to another. But underneath all those transformations, the total amount stayed the same. Energy was conserved. That was the bedrock. That was the rule that could not be broken. In classical physics, energy came in a few standard flavors. There was kinetic energy, the energy of motion, a cannonball flying through the air, a river rushing downhill, your fist moving toward a wall. The faster something moved, the more kinetic energy it carried. The formula was simple. 1/2 times mass times velocity squared. Double the speed and you quadruple the energy. That relationship alone explained why car crashes get so much worse at highway speeds. Then there was potential energy, the energy of position. A boulder perched at the top of a hill, a drawn bow, a coiled spring. The energy was not doing anything yet, but it was there, waiting. Lift a book off the ground, and you have done work against gravity. That work gets stored as potential energy in the book's new position. Let go, and gravity converts that potential back into kinetic as the book accelerates toward the floor. The cycle was clean, predictable, reversible in principle. Heat was another form, thermal energy. The random jittering motion of atoms and molecules inside matter. Rub your hands together and friction converts the organized motion of your palms into the disorganized motion of countless tiny particles. Your hands warm up. The energy has not vanished. It has simply changed shape. Work was the transfer of energy by force. Push a crate across a floor and you are doing work. The energy leaves your muscles, gets transferred through your hands into the crate, and shows up as kinetic energy in the crate's motion or as heat in the friction between the crate and the floor. Energy moved, energy transformed, but the total, if you added up every piece carefully, stayed constant. That principle, the law of conservation of energy, was not obvious. It took decades of careful experiments to establish. In the mid-1800s, several scientists working independently arrived at the same conclusion. Julius Robert Mayer, a German physician, noticed that sailors' blood looked redder in the tropics and hypothesized that the body's energy balance depended on temperature. James Prescott Joule, an English brewer turned physicist, ran meticulous experiments showing that mechanical work and heat were interchangeable. Hermann von Helmholtz, a German polymath, formalized the idea mathematically and extended it to every known physical process. By the 1860s, conservation of energy had become one of the central pillars of physics, a rule so fundamental that violating it would require rewriting reality itself. The beauty of the conservation law was its universality. It did not matter what kind of process you were looking at: a falling rock, a burning log, a steam engine, a chemical reaction. Energy might change forms, might move from place to place, but the total remained fixed. The universe, it seemed, was running on a budget, and the budget always balanced. This picture encouraged a particular way of thinking about energy. It was continuous, smooth, infinitely divisible. You could have 1 joule of energy, or half a joule, or 1/1,000,000th of a joule, or any fraction you liked, all the way down. There was no smallest unit, no fundamental chunk. Energy was like a perfectly smooth liquid that could be poured into containers of any size. You could transfer as much or as little as you wanted. The mathematics reflected this. In every classical equation, energy appeared as a variable that could take any value on the number line. No gaps, no steps, just a continuous sweep from zero to infinity. That metaphor, energy as a flowing substance, was more than a teaching tool. It shaped how physicists thought about the world. When they talked about energy moving from one object to another, they imagined it literally flowing, the way water flows through a pipe, or the way heat spreads through a metal rod. The language was intuitive, it felt right, and for a long time it worked. Then came light. Light had been a puzzle for centuries. Newton thought it was made of particles, tiny corpuscles flying through space. Others, including Christian Huygens, argued it was a wave. By the early 1800s, experiments by Thomas Young and Augustin Jean Fresnel had tipped the scales decisively toward the wave picture. Light interfered with itself. It diffracted around corners. It behaved exactly the way water waves behave when they pass through narrow openings or overlap with each other. Waves, not particles. The debate seemed settled. The final triumph came in 1864 when James Clerk Maxwell published his equations for electricity and magnetism. Maxwell had been trying to unify two seemingly separate phenomena, electric fields and magnetic fields. He found that they were not separate at all. They were two faces of the same thing. A changing electric field generated a magnetic field. A changing magnetic field generated an electric field. The equations described a kind of dance, each field creating the other in a self-sustaining loop. And when Maxwell worked through the math, he realized something extraordinary. The equations predicted the existence of waves made of oscillating electric and magnetic fields rippling through empty space. And the speed of those waves, calculated directly from the equations, matched the speed of light. Exactly. Light was an electromagnetic wave, not an analogy, not a metaphor. Light was literally a ripple in the electromagnetic field, propagating through the vacuum at 300 million meters per second. The equations predicted it, experiments confirmed it. And for a generation of physicists, it felt like the culmination of centuries of effort. Electricity, magnetism, and light were unified under a single elegant framework. The universe was making sense. Maxwell's equations reinforced the classical picture of energy as continuous. A light wave, according to the equations, carried energy smoothly distributed across space. The energy density depended on the strength of the electric and magnetic fields, and those fields could oscillate with any amplitude you liked. A dim light, a bright light, anything in between. The energy could be adjusted continuously, the way you adjust the volume on a radio. There was no hint anywhere in Maxwell's framework that energy might come in discrete pieces. Everything seemed to fit. Newtonian mechanics explained motion. Thermodynamics explained heat and work. Maxwell's equations explained light and electromagnetism, and the law of conservation of energy tied it all together into one coherent system. The classical worldview was not just successful, it was triumphant. It had survived every experimental test thrown at it. It made predictions that came true. It powered the Industrial Revolution. Steam engines, railroads, telegraphs, electric lights, all of it rested on the principles of classical physics. Energy was conserved, energy was continuous, energy flowed, and then someone pointed a thermometer at a glowing piece of metal and the whole thing started to crack. The problem was blackbody radiation. A blackbody, in physics, is an idealized object that absorbs all light falling on it and emits light based purely on its temperature. No material is a perfect blackbody, but many things come close. A lump of iron heated in a forge, the filament in an incandescent bulb, the surface of a star. As you heat a blackbody, it glows. First a dull red, then orange, then yellow, then white. The color shifts because the spectrum of emitted light changes with temperature. Hotter objects emit more light at shorter wavelengths. That much was obvious just from watching a blacksmith's forge. By the late 1800s, physicists had developed instruments sensitive enough to measure the blackbody spectrum in detail. They could plot the intensity of emitted light as a function of wavelength for objects at different temperatures. The curves they measured had a characteristic shape. At very long wavelengths, the intensity was low. As the wavelength decreased, the intensity rose to a peak, then fell off again at short wavelengths. The peak shifted to shorter wavelengths as the temperature increased. Every blackbody, regardless of what it was made of, produced the same shape of curve at a given temperature. That universality suggested something fundamental was going on. Physicists tried to explain the curves using classical theory. The approach was straightforward. A hot object contains charged particles, electrons and ions, jiggling around because of thermal energy. Those jiggling charges act like tiny antennas, radiating electromagnetic waves. The hotter the object, the more violently the charges jiggle, and the more energy they radiate. By applying the principles of thermodynamics and electromagnetism, you should be able to calculate the spectrum. Several people tried. The first successful attempt came from Wilhelm Wien in 1896. Wien derived a formula that matched the experimental data reasonably well at short wavelengths, but it failed at long wavelengths. In 1900, Lord Rayleigh and James Jeans took a different approach. They used the principle of equipartition, a cornerstone of classical statistical mechanics. Equipartition said that every mode of vibration in a system should, on average, carry the same amount of thermal energy. For electromagnetic waves inside a cavity, there are infinitely many possible modes, one for each possible wavelength. Each mode should carry energy proportional to temperature. Add them all up and you get the total radiated energy. The Rayleigh-Jeans law worked beautifully at long wavelengths. It matched the experimental curves perfectly, but at short wavelengths, it went catastrophically wrong. According to the formula, the intensity should keep rising as the wavelength got shorter. It should rise without limit. As you move toward the ultraviolet end of the spectrum and beyond, the predicted energy density climbed toward infinity. Every hot object, according to classical theory, should be radiating infinite energy at short wavelengths. A glowing ember should flood the room with deadly ultraviolet and X-rays. A warm cup of tea should kill you. Obviously, that does not happen. The name given to this disaster was the ultraviolet catastrophe. It was not a small discrepancy. It was not a matter of tweaking a constant or adding a correction term. The classical theory, when applied honestly and carefully, predicted something absurd. And the absurdity was not in the math. The math was fine. The absurdity was in the assumptions. Somewhere deep in the foundation of classical physics, something was wrong. For a while, people tried to patch it. Maybe there was some damping mechanism that suppressed the high-frequency modes. Maybe the cavity walls imposed some constraint that classical theory had overlooked. But none of the fixes worked. The experimental data was clear. Real blackbodies did not radiate infinite energy. The intensity rose to a peak and then fell off smoothly at short wavelengths, exactly as Wien's formula suggested. But Wien's formula had no theoretical justification. It was an empirical fit, not a derivation. And the Rayleigh-Jeans law, which did have a solid theoretical foundation, was simply wrong. The situation was humiliating. Here was one of the simplest, most fundamental phenomena in nature. A hot object glowing in the dark, and the most advanced physics of the age could not explain it. Not approximately, not with some small error. It could not explain it at all. The theory predicted infinity. Reality produced a smooth curve. Something had to give. The classical picture of energy, the picture of a continuous flowing quantity that could be divided and transferred in arbitrarily small amounts, was about to die. Not because someone disproved it philosophically, not because a new theory came along and looked prettier, but because when you pointed that picture at a glowing piece of metal and asked it to predict what you would see, it told you the metal should be emitting infinite energy, and that was not a prediction you could ignore. What replaced it was stranger than anyone expected, stranger than most physicists were willing to accept. And the man who made the first cut into the classical worldview did so reluctantly, almost apologetically, as though he knew he was opening a door that could not be closed. His name was Max Planck, and in 1900 he wrote down a formula that worked. Max Planck did not set out to break physics. He was not a revolutionary by temperament. He was a careful man, methodical, conservative in his approach to science. The kind of physicist who believed that the great work of the field had already been done and that his own generation's job was to clean up the remaining details. He had been told, early in his career, that physics was essentially finished. There were a few loose ends, a few minor puzzles, but the fundamentals were settled. Energy was conserved. Motion obeyed Newton's laws. Light was a wave. Thermodynamics explained heat. The system worked. And then he spent years staring at the black-body radiation problem, trying to make the experimental curves match the theoretical predictions, and nothing worked. The Rayleigh-Jeans law predicted infinity. Wien's formula fit the data, but had no solid foundation. And Planck, who valued rigor and derivation above all else, could not stomach a formula that worked by accident. He needed to understand why it worked. He needed to derive it from first principles. In the autumn of 1900, after months of frustration, Planck tried something desperate. He made a guess. Not a guess about the physics exactly. A guess about the mathematics. He borrowed a trick from statistical mechanics, a field he had spent much of his career dismissing. The trick involved dividing energy into small but finite chunks during the calculation, adding everything up, and then taking the limit as the chunk size went to zero. It was a standard mathematical procedure, a way to turn a sum into an integral. You were not supposed to get a different answer depending on whether you summed first or integrated first. The two methods should give the same result, except this time they did not. When Planck divided the energy into chunks, worked through the algebra, and compared the result to the experimental data, the formula matched perfectly across the entire spectrum, short wavelengths, long wavelengths, every temperature. The curve that came out of his calculation was identical to the curve physicists had been measuring in laboratories for years. He had solved the black-body problem. But there was a catch. The formula only worked if he did not take the limit, if he kept the energy chunks finite, if he treated energy as though it came in discrete packets rather than as a smooth, continuous quantity. That should not have mattered. The size of the chunks was supposed to be arbitrary, a mathematical convenience that disappeared in the final result. But in Planck's formula, the chunk size did not disappear. It stayed in the equation as a constant. A very small constant, but a constant nonetheless. He called it h. It appeared in the formula as the ratio of energy to frequency. For any given frequency of light, the energy had to be an integer multiple of h times that frequency. You could have one packet of energy, or two packets, or three, but you could not have 1.5. Energy was quantized. Planck presented his result to the German Physical Society on December 14, 1900. He derived the formula, showed how it matched the data, and explained the mathematical steps. He did not dwell on the physical interpretation. He did not announce that he had discovered a new law of nature. He framed it as a working hypothesis, a provisional assumption that happened to produce the right answer. The audience received it politely. The formula worked. That was enough for now. But Planck himself was not satisfied. He spent the next several months trying to find a way to derive the same result without the quantization assumption. He tried different mathematical approaches. He re-examined the statistical mechanics. He looked for loopholes, alternative interpretations, anything that would let him recover the continuous picture of energy that classical physics demanded. He found nothing. Every path he tried either led back to quantization or produced the wrong answer. By the spring of 1901, he had accepted, reluctantly, that the quantization was not a mathematical artifact. It was a physical requirement. Energy, at least in the context of black-body radiation, could only be emitted or absorbed in discrete amounts. The smallest possible packet of energy for light of a given frequency was h times that frequency. You could not split it smaller. You could not transfer half a quantum. The universe, it seemed, was running on a grid. The constant h, which would later be called Planck's constant, had a value of approximately 6.626 times 10 to the negative 34 joule seconds. That is a genuinely tiny number. To put it in perspective, a joule is the amount of energy needed to lift a small apple 1 meter off the ground. A joule second is even stranger because it mixes energy and time in a way that does not correspond to any everyday experience. The units themselves hint at something odd happening beneath the surface of reality. Because the constant is so small, the quantization of energy is invisible in everyday life. When you turn on a light, billions upon billions of photons stream out every second. Each one carries a tiny quantum of energy, but there are so many of them that the flow looks perfectly smooth. It is like watching sand pour through an hourglass. Zoomed out, it looks like a continuous stream. Zoomed in, you see individual grains. Planck had found the grains. The size of each quantum depends on the frequency. Higher frequency means higher energy per quantum. For visible light, a single photon carries an energy of around a few electron volts. An electron volt is another tiny unit, roughly 1.6 times 10 to the negative 19 joules. For radio waves, the energy per photon is far smaller, sometimes thousands or millions of times less. For X-rays and gamma rays, the energy per photon is much larger, enough in some cases to ionize atoms and break chemical bonds. The relationship is direct and unforgiving. Double the frequency and you double the energy of each quantum. The frequency of visible light sits around 500 trillion cycles per second, 5 times 10 to the 14th hertz. Multiply that by Planck's constant and you get the energy of a single photon of green light. This was not what anyone expected. Classical physics had no room for a smallest unit of energy. Energy was supposed to be a continuum, something you could divide forever. And yet here was a formula derived from the experimental data that said otherwise. Energy came in chunks. Not because of some limitation in our measuring instruments, not because of some quirk in the experimental setup, but because that was how energy actually behaved at small scales. The flow was an illusion. The grid was real. Planck was disturbed by his own result. He did not like the idea that energy was quantized. It violated his intuition. It conflicted with everything he had been taught about how the world worked. For the rest of his life, he would describe the quantum hypothesis as an act of desperation, something he had stumbled into because nothing else worked. He was not celebrating a breakthrough, he was apologizing for it. The reaction from the broader physics community was muted. The formula was useful. It solved a real problem. But most physicists treated it the way Planck himself had initially treated it, as a mathematical trick rather than a statement about physical reality. Maybe energy was not really quantized. Maybe the quantization was just an artifact of how energy was exchanged between matter and light. Maybe there was some deeper, still classical explanation waiting to be found. For several years, Planck's constant was a number you plugged into an equation to get the right answer. It was not yet a revolution. The first person to take Planck's idea seriously, to treat it as a literal description of nature rather than a calculational convenience, was not Planck. It was a young patent clerk in Switzerland named Albert Einstein. And Einstein did not apply the quantum idea to blackbody radiation. He applied it to light itself. He took Planck's reluctant hypothesis and pushed it further than Planck had dared to go. He said that light did not just interact with matter in discrete chunks. Light was made of discrete chunks. The electromagnetic wave that Maxwell had described so elegantly was not the whole story. Light was also a particle, a quantum of energy traveling through space as an indivisible unit. That was 1805. The photoelectric effect, we will get to that. But for now, the point is that Planck had cracked the door open and Einstein kicked it off its hinges. What started as a narrow fix for a specific problem in thermal radiation became the foundation for an entirely new framework, quantum mechanics. A theory that would eventually explain atoms, chemical bonds, semiconductors, superconductors, the structure of matter, the behavior of light, and the fundamental limits of measurement itself. All of it traced back to that one uncomfortable fact. Energy does not flow smoothly. It jumps. The implications were staggering once people started to unpack them. If energy is quantized, then so is everything that depends on energy. The vibrations of atoms in a crystal, the rotation of molecules, the orbits of electrons around nuclei, all of it had to come in discrete steps. You could not have a continuous range of possibilities. You had to have specific allowed states separated by gaps. An electron in an atom could not orbit at any distance it liked. It had to sit in one of a small number of permitted orbits. When it jumped from one orbit to another, it emitted or absorbed a quantum of light with exactly the right frequency to match the energy difference between the two orbits. That explained the spectral lines that chemists and astronomers had been cataloging for decades. Each element produced its own unique pattern of lines because each element had its own unique set of allowed electron orbits. The lines were not just a fingerprint, they were a map of the quantum structure of the atom. Planck himself was slow to accept the full implications of his discovery. Even as quantum mechanics developed through the 1910s and 20s, Planck remained cautious. He had opened the door, but he was not sure he wanted to walk through it. Other physicists, younger and less attached to the classical worldview, charged ahead. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Louis de Broglie, Max Born. They built the machinery of quantum mechanics, layer by layer, each new insight more bizarre than the last. Particles behaving like waves, waves behaving like particles. Uncertainty principles that placed hard limits on what could be known, probability replacing determinism at the heart of physical law. All of it rested on the idea that energy, the fundamental currency of the universe, was not infinitely divisible. The resistance to quantum mechanics was fierce, not because the math was wrong. The math worked beautifully. The predictions matched experiments with absurd precision. But the interpretation, the picture of reality that the math seemed to demand, was deeply unsettling. Einstein, despite having helped launch the quantum revolution, spent the latter half of his career arguing against its philosophical implications. He accepted that quantum mechanics was useful. He accepted that it made correct predictions, but he did not accept that it was complete. He believed there had to be a deeper layer of reality underneath, something deterministic and continuous, something that would restore the classical picture once we figured out how to look at it properly. He was wrong. Every experiment designed to find that deeper layer came up empty. Quantum mechanics was not a placeholder, it was the answer. By the 1930s, the evidence was overwhelming. Energy was quantized, matter was quantized, light was quantized. The universe at its smallest scales did not run on smooth curves. It ran on a lattice of discrete states separated by gaps too small for human senses to detect, but large enough to completely change the rules. The classical world, the world of flowing energy and continuous motion, was a large-scale approximation, an illusion that emerged when you added up trillions of tiny quantum jumps and averaged over timescales too short to perceive. Zoomed out, the lattice looked smooth. Zoomed in, the steps were undeniable. Planck's constant became one of the most important numbers in physics. It set the scale for quantum effects. Any process involving energies or distances comparable to h was guaranteed to behave in ways that classical physics could not explain. It appeared in the uncertainty principle, which said you could not measure both the position and momentum of a particle with perfect precision at the same time. The more accurately you measured one, the less accurately you could know the other. The product of the uncertainties had to be at least as large as Planck's constant divided by 4 pi. That was not a limitation of your equipment. That was a limitation of reality. The universe itself did not contain enough information to specify both quantities exactly. Planck's constant also set the boundary between the quantum world and the classical world. For objects much larger than atoms, for energies much larger than a few electron volts, the quantum effects averaged out and classical physics took over. A baseball flying through the air did not care about quantization. The uncertainties were so small compared to the ball's size and momentum that they disappeared into the noise. But shrink the system down, look at individual atoms, individual photons, and the quantum nature of energy became unavoidable. The world stopped being smooth. It became grainy, jittery, probabilistic. The kind of place where particles could tunnel through barriers they did not have enough energy to climb over, where identical particles could interfere with themselves, where the act of measuring something could change its state. None of this was speculation. It was tested, confirmed, refined, and applied. Quantum mechanics became the foundation for modern technology. Semiconductors, lasers, magnetic resonance imaging, atomic clocks, electron microscopes, solar cells. Every piece of technology that relies on controlling electrons or photons at small scales is built on the principles Planck stumbled into while trying to fix a curve. His desperate guess became the bedrock of an entire branch of science, and yet the strangeness never went away. Quantum mechanics works. It works better than any other theory in the history of physics, but it does not feel right. It does not match our intuition. We evolved to deal with objects we can see and touch, objects that behave in predictable, continuous ways. We did not evolve to think about particles that exist in multiple states at once until someone looks at them. We did not evolve to picture energy as coming in irreducible lumps. Our brains want the world to be smooth. The world is not. Planck died in 1947, just after the end of the Second World War. By then, quantum mechanics was 30 years old and thoroughly mainstream. It had survived every experimental test. It had explained phenomena that classical physics could not touch, and it had produced technologies that changed the world. Planck lived long enough to see his reluctant hypothesis become one of the central pillars of modern science, but he never fully reconciled himself to it. He remained, until the end, a classical physicist at heart, uncomfortable with the world he had helped reveal. The quantum revolution did not stop with Planck. It accelerated. The next step came when someone took the quantum idea and applied it not just to the emission and absorption of light, but to light itself. That someone was Einstein, and the phenomenon was simple enough that you could demonstrate it with a battery, a metal plate, and a beam of light. No enormous telescopes, no particle accelerators, just light hitting metal and knocking electrons loose. Except classical physics said it should not work the way it did. The electrons should have absorbed energy gradually, like a sponge soaking up water. Instead, they popped out instantly, as though they had been hit by tiny bullets. Planck had found that energy was quantized when it was exchanged. Einstein found that light itself was made of those quanta, not just a wave, a particle, a photon. And that changed everything again. Einstein did not discover the photoelectric effect. That honor belongs to Heinrich Hertz, who noticed it by accident in 1887 while conducting experiments on electromagnetic waves. Hertz was trying to prove Maxwell's theory of electromagnetism. He had built a spark gap transmitter and a loop of wire with another tiny spark gap to act as a receiver. When a spark jumped across the transmitter, the receiver sparked too, even though the two were not physically connected. Electromagnetic waves were traveling through empty space, exactly as Maxwell had predicted. Hertz was ecstatic. He had proven that light was a wave, but he noticed something odd. When ultraviolet light shone on the metal electrodes of his spark gap, the sparks came more easily. The light seemed to be helping the electricity jump the gap. Hertz noted the observation, published it, and moved on. He did not think it was particularly important. He was hunting bigger game. Over the next 2 decades, other physicists poked at the effect. They put the metal electrodes in vacuum chambers to eliminate air resistance. They measured the currents. They varied the light intensity, the color, the type of metal, and slowly a pattern emerged that made no sense at all. When light hit certain metals, electrons were ejected from the surface. That much was fine. Light carried energy, so it seemed reasonable that it could knock electrons loose. But the details were wrong, completely wrong. Classical physics predicted that if you shone light on a metal, the electrons would gradually absorb energy from the electromagnetic wave until they had soaked up enough to escape the surface. Brighter light should mean faster absorption and faster ejection. Dim light should still work, it would just take longer, and the energy of the ejected electrons should depend on the intensity of the light. Shine a brighter light, and the electrons should fly out faster. Shine a dimmer light, and they should dribble out slowly. None of that happened. What actually happened was this: if you used red light, no matter how bright you made it, no electrons came out. Zero. You could blast the metal with an industrial searchlight's worth of red photons, and the metal would sit there, utterly unbothered, refusing to emit a single electron. Then you could switch to ultraviolet light, even an extremely faint beam, and electrons would start popping out immediately, instantly, not after a delay while they absorbed energy. The moment the ultraviolet light hit the surface, electrons appeared. The energy of those electrons did not depend on the brightness of the light, it depended on the color. Blue light produced faster electrons than red light, assuming red light worked at all, which it usually did not. Ultraviolet light produced even faster electrons. And if you increased the intensity of the light without changing its color, you did not get faster electrons. You got more electrons. More particles flying out, but each one moving at the same speed as before. This was absurd. A wave does not work that way. If you are standing in the ocean and a wave hits you, a bigger wave knocks you over harder. A smaller wave barely moves you. The effect is continuous, smooth, proportional to the amplitude. But the photoelectric effect was not continuous. It had a threshold. Below a certain frequency, nothing happened. Above that frequency, electrons appeared, and their energy depended only on the frequency of the light, not on how much light you were shining. Experiments by Philipp Lenard in the early 1900s mapped the effect in detail. Lenard was meticulous and his data was clean. He showed that every metal had a specific threshold frequency. For light below that frequency, no electrons were emitted no matter how long you waited or how bright the light was. For light above that frequency, electrons appeared immediately and their maximum kinetic energy increased linearly with the frequency of the light. He also showed that increasing the intensity increased the number of electrons, but did not change their energy. The wave theory could not explain any of it. The problem was the delay, or rather the lack of one. If light was a wave spreading its energy evenly across space, then when that wave hit a metal surface, the energy should be distributed across a large number of atoms. Each electron should absorb a tiny fraction of the total energy. To accumulate enough energy to escape, an electron would need to sit there soaking up wave energy for minutes, maybe hours, depending on the intensity of the light. And yet electrons appeared instantly, even under faint illumination. The math did not work. If you calculated how long an electron should need to absorb enough energy from a dim beam of light to escape, you got times measured in hours or days. In reality, the delay was less than a billionth of a second. Einstein looked at this mess in 1905 and saw an opportunity. He had been thinking about Planck's work on blackbody radiation. Planck had quantized the exchange of energy between light and matter. Einstein took it a step further. He proposed that light itself was quantized, not just when it was emitted or absorbed, but all the time. Light, he said, was not a continuous wave. It was a stream of particles, discrete packets of energy flying through space. Each packet carried an amount of energy equal to Planck's constant times the frequency of the light. E equals h times nu. Higher frequency meant higher energy per packet. Lower frequency meant lower energy. He called them light quanta. The word photon came later, coined by a chemist named Gilbert Lewis in 1926. Though Lewis's own theory about photons turned out to be wrong, the name stuck anyway. Einstein did not care much about names. He cared about the explanation, and his explanation was brutally simple. When a light quantum hit an electron, it gave the electron all of its energy in a single transaction, all or nothing. No gradual absorption, no wave spreading energy across multiple atoms. One photon, one electron, one instant transfer of energy. If the photon's energy was greater than the work function, the minimum energy needed to free an electron from the metal's surface, then the electron escaped. Any leftover energy became kinetic energy, and the electron flew away at high speed. If the photon's energy was less than the work function, nothing happened. The electron absorbed the photon, sure, but it did not have enough energy to escape, so it stayed put and the energy dissipated as heat. That explained the threshold. Light below a certain frequency simply did not carry enough energy per photon to knock electrons loose. It did not matter how many photons you sent, each one failed individually. Pile 1,000,000 too small photons onto a single electron, and you still got nothing, because the electron could only interact with one photon at a time. Brighter light meant more photons per second. More photons meant more collisions. More collisions meant more electrons ejected. But each electron still got its energy from a single photon, so the energy of each electron depended only on the frequency of the light, not the intensity. The linear relationship between frequency and electron energy fell straight out of the equation. E equals h nu minus the work function. The work function was a constant for a given metal. The frequency was under your control. Change the color of the light, and you changed the energy of the ejected electrons in exact proportion. The fit with Lenard's data was perfect. Einstein's paper was published in March 1905 in a German journal called Annalen der Physik. It was one of 4 papers he published that year, a stretch of productivity so absurd that physicists still refer to 1905 as Einstein's miracle year. One paper explained Brownian motion and provided some of the most convincing evidence yet that atoms were real. Another introduced the special theory of relativity and rewrote our understanding of space and time. A third showed that mass and energy were equivalent, E equals mc squared, possibly the most famous equation in history. And the fourth, the one on the photoelectric effect, proposed that light was made of particles. The reaction was mixed. The photoelectric paper was the only one of the 4 that explicitly challenged the existing framework of physics. Relativity was strange, but it did not contradict Maxwell's equations. It extended them. The photon idea, on the other hand, seemed to contradict Maxwell directly. Light was a wave. Maxwell had proved it. Hertz had confirmed it. Interference, diffraction, polarization, every experiment ever done on light showed wave behavior, and now Einstein was saying light was also a particle. Not that it behaved like a particle in certain situations, that it was a particle. How could something be both? Most physicists ignored the paper. Relativity got attention. The photoelectric paper did not. Even Planck, who had started the whole quantum business, thought Einstein had gone too far. Planck respected Einstein, admired his work on relativity, and later helped bring him to Berlin, but he considered the light quantum idea a mistake. In 1913, when a group of prominent physicists wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences, they included an apology for the photon hypothesis. They wrote that Einstein had occasionally missed the target in his speculations, as for example in his hypothesis of light quanta. That was 8 years after the photoelectric paper. Einstein had proposed the photon in 1905, and by 1913 the scientific establishment still thought he was wrong about it. The holdout lasted another decade. Slowly, experimental evidence accumulated. Robert Millikan, an American physicist, spent 10 years from 1912 to 1923 trying to disprove Einstein's photoelectric equation. Millikan did not believe in photons. He thought the wave theory of light was correct, and that Einstein's formula, while it happened to fit the data, must be a coincidence or an approximation that would break down under more careful measurement. So he designed meticulous experiments, refined his techniques, eliminated every possible source of error, and measured the photoelectric effect with extraordinary precision. The result was that Einstein's equation held up perfectly. Millikan confirmed it to within a fraction of a percent. The relationship between frequency and electron energy was exactly what Einstein had predicted. Millikan won the Nobel Prize in 1923 for his experimental work. In his Nobel lecture, he admitted that the data supported Einstein's equation but said he still did not believe the underlying theory. The photon, in his view, was still a convenient fiction. Einstein received the Nobel Prize 2 years earlier in 1921, though the award was not announced until 1922 because the committee could not decide whether his work deserved it. When they finally gave in, they cited the photoelectric effect, not relativity. Relativity was still considered controversial. The photon, despite Millikan's protests, was at least experimentally verified. The committee's official statement was carefully worded. They gave Einstein the prize for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. They did not say he had discovered the photon. They said he had discovered a law, a formula. They were hedging. By the mid-1920s, the evidence was overwhelming. Arthur Compton's experiments on X-ray scattering in 1923 showed that when X-rays collided with electrons, they behaved exactly like particles bouncing off other particles. The X-rays transferred momentum, they changed direction. They lost energy in precise amounts that matched the predictions of particle collisions. Compton won the Nobel Prize for that work in 1927. The photon was real. Light was a particle. Except it was also still a wave. The interference patterns did not go away. You could still send light through two slits and get alternating bright and dark bands on a screen, a pattern that only made sense if light was a wave that could interfere with itself. And now you also had experiments showing that light came in discrete chunks that collided with electrons like billiard balls. Both descriptions were correct, both were verified, and they were completely incompatible. A particle is a localized thing. It has a position. You can point to it and say it is here, not there. A wave is spread out. It exists in many places at once. How could light be both? The answer, as it turned out, was that light was neither, or both, or something else entirely that human language did not have words for. The best you could say was that light exhibited particle-like behavior in some experiments and wave-like behavior in others. Which behavior you saw depended on what you measured. If you designed an experiment to detect particles, you got particles. If you designed an experiment to detect waves, you got waves. The photon was not a tiny ball. It was not a ripple in a medium. It was a quantum object, something that did not map cleanly onto any classical concept. The word photon was just a label we attached to that object when it was doing particle-like things. The properties of a photon are strange even by quantum standards. It has zero rest mass, literally zero. Not a small mass, not a negligible mass, zero. If a photon were ever at rest, which it never is, it would weigh nothing. But photons are never at rest. They move at the speed of light, always, in every reference frame. That is the only speed they have. They cannot slow down, they cannot speed up. They are created moving at light speed, and they stay at that speed until they are absorbed. Because they have no rest mass, photons do not experience time the way massive particles do. From a photon's perspective, if you could somehow ride along with one, the journey from emission to absorption takes zero time. A photon emitted by a star 10 billion light-years away and absorbed by your eye billions of years later experiences no passage of time between those events. The universe ages, the photon does not. This is not mysticism, it is a direct consequence of special relativity. At light speed, time dilation becomes infinite. Clocks moving at light speed do not tick. Photons do carry energy, lots of it in some cases. The energy depends on frequency, E equals h nu. Plug in the frequency and you get the energy. For visible light, a single photon carries a few electron volts. That is enough to trigger a chemical reaction in your retina, which is how you see. For radio waves, the energy per photon is far smaller, millions or billions of times less. For gamma rays, the energy per photon can be enormous, enough to rip atoms apart and damage DNA. The difference between a radio wave and a gamma ray is not just intensity, it is the energy per quantum. Photons also carry momentum, even though they have no mass. That seems like a contradiction, but it is not. In classical physics, momentum is mass times velocity. In relativity, momentum is more general. It is related to energy. For a photon, the momentum is the energy divided by the speed of light, P equals E over c. It is a small amount of momentum for typical photons, but it is real. You can measure it. When a photon hits a surface and gets absorbed, it transfers its momentum to that surface. The surface feels a tiny push. Enough photons and the push adds up. This is radiation pressure. It is the reason comet tails point away from the sun. Sunlight hitting dust particles in the comet's coma pushes them outward, away from the sun's direction. The push is gentle, but over time and distance, it is enough to create the spectacular tails we see from Earth. Photons interact with matter in only a few ways. They can be absorbed, which means an electron or atom takes the photon's energy and the photon ceases to exist. They can be emitted, which is the reverse process. An electron drops to a lower energy state and a photon appears, carrying away the energy difference. Or they can scatter, bouncing off particles and changing direction. Each interaction is a discrete event. A single photon, a single electron, a single transaction, no gradual buildup, no partial exchanges. Quantum mechanics does not do halfway. The wave-particle duality is not limited to light. In 1924, a French physicist named Louis de Broglie proposed that if light, which everyone thought was a wave, could behave like a particle, then maybe particles, which everyone thought were particles, could behave like waves. He wrote down a formula for the wavelength of a particle. Lambda equals h over p, where p is the momentum. Planck's constant showed up again, setting the scale. For large objects, the wavelength is absurdly tiny, far too small to measure or matter. For electrons, which are light and often moving fast, the wavelength is comparable to the size of atoms, and that means electrons can diffract, interfere, and do all the other things waves do. De Broglie's idea was tested in 1927 by Clinton Davison and Lester Germer, who fired electrons at a crystal of nickel and saw a diffraction pattern. Electrons, indisputably particles with mass and charge, were behaving like waves. George Paget Thomson, working independently, got similar results by passing electrons through thin metal films. Thomson won the Nobel Prize for proving the electron was a wave. His father, J.J. Thomson, had won the Nobel Prize 30 years earlier for proving the electron was a particle. Both were right. By the late 1920s, the duality was accepted as a core feature of quantum mechanics. Particles were waves. Waves were particles. The distinction was a relic of classical thinking. At the quantum level, everything was described by a wave function, a mathematical object that encoded probabilities. When you measured a particle's position, the wave function collapsed and you got a definite location. When you measured its momentum, you got a definite velocity. But before the measurement, the particle did not have a definite position or a definite momentum. It had a range of possibilities, a spread, a cloud of probability. The wave function told you the shape of that cloud. The photon fit into this picture as a quantum of the electromagnetic field. The field itself was the fundamental thing. The photon was an excitation of that field, a ripple, a localized packet of energy. When you detected a photon, you were detecting the field in a specific state. The field was always there, even in empty space. The photon was what happened when the field carried energy. This language, fields and excitations, became the foundation for quantum field theory, the framework that describes all of particle physics. Every particle is a quantum of some field. Electrons are quanta of the electron field. Quarks are quanta of quark fields. Photons are quanta of the electromagnetic field. The universe is not made of particles moving through space. It is made of fields filling space, and particles are what we see when those fields are excited. Einstein saw the beginning of this picture in 1905. He did not have the full theory. Quantum field theory would not be developed for another few decades, but he had the key insight. Light was quantized, energy came in packets, and those packets behaved like particles when you looked at them the right way. He spent the rest of his life uncomfortable with where that insight led. He believed quantum mechanics was incomplete. He thought there had to be something deeper, some hidden layer of reality that would restore determinism and make the wave function collapse go away. He was probably wrong about that. Every test of quantum mechanics has confirmed that the probabilities are fundamental, not just a reflection of our ignorance. But he was absolutely right about the photon. Light is a particle. It is also a wave. It is a quantum object that does not fit into the boxes we inherited from classical physics. It moves at the universe's speed limit, carries energy and momentum, and interacts with matter in discrete chunks. It is the messenger that brings information from distant stars, the carrier of the electromagnetic force, and the reason you can see these words right now. Trillions of photons are streaming from your screen into your eyes every second, each one a tiny packet of energy that left the screen a few nanoseconds ago and arrived at your retina without aging, without slowing, without changing in any way except to be absorbed. And in that absorption, a molecule in your retina changes shape, triggering a cascade of signals that ends with a thought forming in your brain. Every photon is the same as every other photon of the same energy, indistinguishable, identical, interchangeable. There is no such thing as a unique photon. You cannot tag one and track it. The question of which photon hit which electron does not even make sense. Photons are not individuals. They are excitations of a single underlying field, and the field is everywhere. When you talk about a photon traveling from here to there, you are really talking about the field being excited here, there, then somewhere else, in a pattern that looks like motion. But the field is not moving. The excitation is moving through the field the way a wave moves through water. The water stays put, the wave travels. The electromagnetic field stays put, the photon travels. This is the curious case of the photon, a particle with no mass that never stops moving, a wave that comes in discrete packets, a quantum of light that somehow carries the information written in the spectrum of a distant galaxy across billions of light years and delivers it intact to a telescope mirror. The photon is the simplest quantum object and also one of the strangest. It forced physicists to abandon the classical picture of light as a continuous wave and accept that energy itself is grainy, discontinuous, quantized. Planck found the graininess in the exchange, Einstein found it in the light, and once the door was open, once the idea that energy came in chunks was taken seriously, the rest of quantum mechanics poured through. The universe was not smooth, it was made of steps, and every step, every quantum jump, was governed by fields that filled space even when nothing was there. Those fields are where the story goes next. The photon solved one problem and created another. If light came in packets, if energy was quantized, if particles could behave like waves and waves could behave like particles, then what exactly was a particle? The question sounds simple. It is not. The answer led physicists into territory so strange that even now, a century later, most people who encounter it for the first time assume someone is either joking or lying, but the evidence is overwhelming. The universe is not made of particles, it is made of fields. And once you understand what that means, once you really grasp the implications, you cannot look at empty space the same way again. Fields are not a quantum invention. They were already part of physics long before anyone worried about photons or wave functions. The idea of a field goes back at least to the 18th century, though it took a long time to become respectable. The problem was action at a distance. When Newton described gravity, he gave a formula for the force between two masses. The force depended on the masses and the distance between them. Plug in the numbers and you got the right answer. But Newton himself was uncomfortable with how it worked. How did the Earth know the moon was there? How did the moon feel the Earth's pull across 250,000 miles of empty space? There was no rope connecting them, no fluid pushing them. The force just appeared instantly across the void. Newton called it absurd. He wrote in his letters that no one with any competence in philosophical matters could believe that one body could act on another at a distance without some intermediary, but he could not find the intermediary. So he gave the formula and left the mechanism as an open question. The same problem came up with electricity and magnetism. Rub a piece of amber and it attracts bits of paper. Hold a magnet near an iron nail and the nail jumps toward it. The objects do not touch. There is empty space between them, and yet something is happening across that space. Michael Faraday, working in the early 1800s, found a way to think about it that made sense. He imagined lines of force stretching through space, connecting the objects. The lines were not real in the sense that you could see them or touch them. They were a way of mapping the influence one object had on another. Around a magnet, the lines formed loops, North Pole to South Pole, filling the space in a definite pattern. Around a charged object, the lines radiated outward or inward depending on the sign of the charge. Faraday called the whole structure a field. The field was the thing that filled the space and transmitted the force. James Clerk Maxwell took Faraday's lines and turned them into equations. Maxwell was a mathematician as well as a physicist, and he saw that the field concept could be made precise. Instead of vague lines, you could assign a number to every point in space. At each location, the field had a strength and a direction. The electric field at a point told you what force a charged particle would feel if you placed it there. The magnetic field told you what torque it would experience. The fields themselves obeyed equations, differential equations, that described how they changed in space and time. A changing electric field created a magnetic field. A changing magnetic field created an electric field. The two were coupled, looping back on each other, and the result was waves, electromagnetic waves traveling at the speed of light. Maxwell had unified electricity, magnetism, and light into a single framework, and at the heart of that framework was the field. The field was not just a bookkeeping device, it was a physical thing. It carried energy, it carried momentum. When you charged a capacitor, energy was stored in the electric field between the plates. When you sent a radio signal, energy traveled through space in the electromagnetic field. The field had properties. It could oscillate, it could interfere with itself, it could be measured. By the late 19th century, most physicists accepted that the electromagnetic field was real. It was not a mathematical fiction. It was part of the furniture of the universe, as real as matter. Gravity was harder. Einstein spent years trying to understand how gravity worked. Newton's formula gave the right answers for most purposes, but it still had the action at a distance problem. And worse, it was incompatible with relativity. In special relativity, nothing could travel faster than light. But Newton's gravity acted instantly. Change the position of the sun and the Earth should feel it immediately, no delay. That violated relativity. Something had to give. Einstein's solution, published in 1915, was general relativity. He described gravity not as a force, but as a curvature of space-time itself. Mass and energy bent space-time. Objects moving through that curved space-time followed paths that looked, from the outside, like they were being pulled by a force. But there was no force. There was geometry. Space-time itself was the field. The gravitational field was not something sitting in space. It was the shape of space. So by the early 20th century, physics had three fields: the electromagnetic field, the gravitational field, and space-time itself, if you wanted to count that separately. Fields were a standard part of the toolkit, but they were still treated as continuous, smooth, infinitely divisible, just like energy had been before Planck. And just like energy, the fields were about to get quantized. The first person to seriously try quantizing a field was Paul Dirac. Dirac was a British physicist, quiet, precise, almost pathologically economical with words. He did not talk much, but when he did, he was usually right. In the late 1920s, Dirac was working on the problem of how to combine quantum mechanics with special relativity. Quantum mechanics, as developed by Schrödinger and Heisenberg, worked beautifully for slow-moving particles. But it did not respect the rules of relativity. When particles moved at speeds close to the speed of light, the equations broke down. Dirac found a way to fix that. He wrote down a new equation, now called the Dirac equation, that described electrons in a way consistent with both quantum mechanics and relativity. The equation was elegant. It predicted the electron's spin. It predicted the existence of antimatter. It was one of the most successful pieces of theoretical physics ever written. But the Dirac equation was strange. It described a single electron, but it had solutions that looked like particles with negative energy. Negative energy states made no sense. If they existed, ordinary electrons should be able to drop into them, releasing energy, and the universe should collapse into a cascade of particles falling into ever lower energy states. Dirac realized that the only way out was to assume all the negative energy states were already filled. There was a kind of sea of negative energy electrons, completely filling the vacuum. Normally you would not notice them because they were everywhere, a uniform background. But if you added enough energy, you could kick one of those negative energy electrons up into a positive energy state. What you would see is the appearance of a normal electron and a hole in the sea where the electron used to be. The hole would behave like a particle with positive charge. Dirain called it an anti-electron. Carl Anderson discovered it experimentally in 1932 by studying cosmic rays. The particle was real. We call it the positron. Dirac's sea worked, but it was awkward. The picture of an infinite ocean of unobservable particles filling space was conceptually messy. The cleaner interpretation came when physicists started thinking about fields instead of particles. Instead of starting with particles and trying to make them obey quantum rules, you could start with a field and quantize the field itself. This was quantum field theory. The idea was to treat the field as the fundamental object. The classical electromagnetic field, for example, could oscillate. At every point in space, the field had a value, and that value could go up and down. In the classical theory, those oscillations were waves. Light was a wave in the electromagnetic field. In the quantum version, you applied the same quantization procedure that Planck and Einstein had used for light, but you applied it to the field itself. The field became an operator, a mathematical object that created and destroyed particles. A particle was an excitation of the field. A photon was the field oscillating at a particular frequency and location. An electron was an excitation of the electron field. A quark was an excitation of a quark field. Every type of particle had its own field, and the field existed everywhere, at every point in space, all the time. This sounds abstract. It is, but the implications are concrete. In quantum field theory, particles are not little balls bouncing around in empty space. They are ripples in an underlying medium. The medium is the field. The ripples are the particles. When you see an electron, you are seeing a localized excitation of the electron field. When the electron moves, the excitation moves through the field. When the electron disappears, absorbed by a nucleus or annihilating with a positron, the excitation in the electron field vanishes and excitations in other fields appear. Energy and momentum are conserved, but the particles themselves are ephemeral. They are patterns, not things. The field is everywhere. That is important. It is not just near the particle. The electron field fills the entire universe. Every cubic centimeter of space, every point from here to the edge of the observable cosmos, contains the electron field. Most of the time, most places, the field is in its ground state, the lowest energy configuration. No excitations, no particles, but the field is still there. When an electron appears, it is not that a new field shows up. It is that the existing field, which was already there, develops a ripple. The ripple is the electron. The same is true for the photon field. The photon field is just another name for the electromagnetic field, quantized. Light is an excitation of that field. In empty space, far from any stars or lamps, the photon field is in its ground state, no light. But the field exists, it is waiting. Send a light wave through that region and you are creating an excitation in the photon field, a ripple. The ripple carries energy and momentum. It moves at the speed of light because that is how excitations in the photon field propagate. When the light is absorbed, the excitation disappears, the field returns to its ground state, the photon is gone, but the field remains. This picture solves a lot of problems. It explains why all electrons are identical. They are excitations of the same field, so of course they look the same. It explains how particles can be created and destroyed. You are not creating or destroying matter in some deep sense. You are adding or removing excitations in a field. It explains interference. When you send a single photon through two slits, it is not that the photon splits or takes two paths. It is that the photon field extends through both slits. The field interferes with itself, creating a pattern of higher and lower probability for where an excitation might be detected on the screen. The particle language and the wave language are both approximations. The field is the reality. Quantum field theory became the foundation for the standard model of particle physics. Every particle in the standard model is an excitation of a corresponding field. Electrons, quarks, neutrinos, photons, gluons, W and Z bosons, the Higgs boson, each one has a field. The fields interact. The interactions are described by additional terms in the equations. When an electron emits a photon, what is happening at the field level is that the electron field and the photon field are coupled. The coupling allows an excitation in the electron field to create an excitation in the photon field. The excitation in the electron field loses energy. The photon field gains energy. We see this as an electron emitting a photon. But at the fundamental level, it is fields talking to each other. The mathematics of quantum field theory is formidable. The calculations involve sums over infinitely many possible processes, integrals over all of spacetime, and techniques for handling infinities that show up in intermediate steps. Renormalization, the process of carefully subtracting infinities to get finite, measurable predictions, is one of the most technically difficult parts of modern physics, but the predictions that come out are astonishingly precise. Quantum electrodynamics, the quantum field theory of electromagnetism, predicts the magnetic moment of the electron to 12 decimal places. It is the most accurately tested prediction in the history of science. The theory works. So what does it mean to say the field is everywhere? Picture a still pond. The surface of the water is flat, no ripples. That is the ground state. Now drop a pebble into the pond. A ripple spreads outward. The ripple is an excitation. It carries energy. It moves across the surface. But the water itself does not travel with the ripple. The water stays put. The ripple is a pattern moving through the water. The photon field is the pond. The photon is the ripple. The difference is that the photon field is not made of water or anything else tangible. It is a mathematical structure. It assigns a value to every point in space. When the value oscillates in a localized way, you get a particle. The ground state of the field is not nothing. This is crucial. In classical physics, empty space was truly empty, a void. No matter, no energy, no anything. In quantum field theory, empty space is the state where every field is in its lowest energy configuration. The fields are still there. They have not gone away. They are just not excited. The vacuum, the term physicists use for empty space, is the state where there are no particles, but it is not the absence of fields. It is the presence of fields in their ground state, and the ground state has energy, not because there are particles in it, but because of the quantum nature of the field itself. Every field is like a collection of harmonic oscillators, one at every point in space. A harmonic oscillator is a system that can vibrate, like a mass on a spring. In classical physics, a harmonic oscillator at rest has zero energy. In quantum mechanics, it has a minimum energy, the 0-point energy, equal to half of Planck's constant times the frequency. That energy cannot be removed. It is a consequence of the uncertainty principle. You cannot have a system with both zero position and zero momentum at the same time. The oscillator has to have some energy just to exist. Every mode of the field, every possible wavelength, has its own 0-point energy. Add them all up, and you get the 0-point energy of the field. And because there are infinitely many modes, the total 0-point energy is infinite. That sounds like a disaster. And in some ways it is. The infinite energy of the vacuum is one of the major unsolved problems in theoretical physics. It shows up as a contribution to the cosmological constant, the term in Einstein's equations that describes the energy density of empty space. Observations tell us the cosmological constant is small. Quantum field theory predicts it should be huge, not just large, huge, 120 orders of magnitude larger than what we measure. That is the biggest mismatch between theory and experiment in the history of physics. Nobody knows how to fix it. The vacuum is strange, but the zero-point energy is real. It has measurable effects. The Casimir effect, discovered experimentally in 1948, is one of the cleanest demonstrations. Take two flat metal plates and place them very close together, a few micrometers apart, in a vacuum. The quantum fields between the plates are restricted. Only certain wavelengths fit in the gap. Outside the plates, all wavelengths are allowed. The result is that there is more zero-point energy outside the plates than inside. The imbalance creates a force. The plates are pushed together. The force is tiny, but it has been measured many times, and it matches the predictions of quantum field theory. The vacuum, even with no particles in it, exerts pressure. Another effect is the Lamb shift. In a hydrogen atom, the electron orbits the nucleus. Quantum mechanics predicts specific energy levels for those orbits. But when you measure the energy levels very precisely, you find tiny shifts that are not in the basic quantum mechanical calculation. The shifts come from the interaction between the electron and the zero-point fluctuations of the photon field. The electron is constantly emitting and reabsorbing virtual photons, excitations of the field that exist for such a short time that they do not violate energy conservation. Those virtual photons slightly change the electron's energy. The effect is small, but it was measured in 1947 by Willis Lamb, and it provided some of the earliest direct evidence that the quantum vacuum was not empty. So empty space is not empty, it is full of fields. The fields are in their ground state, but the ground state is active. It fluctuates, it has energy, it interacts with particles. When you look at a region of space with no particles, no light, no nothing, you are looking at the lowest energy state of every field that exists. The electron field is there, the photon field is there, the quark fields, the gluon field, the Higgs field, all of them, overlapping, coexisting, each one extending through the entire universe. The fields do not block each other, they occupy the same space. They are different aspects of the same underlying reality. This is the quantum field picture. It is not optional, it is not a philosophical interpretation. It is the framework that explains every confirmed result in particle physics. When you collide protons at the Large Hadron Collider and new particles spray out, you are not breaking the protons into pieces, you are dumping energy into the quantum fields. The energy creates excitations. Those excitations are the particles you detect. When a particle decays, the excitation in one field disappears and excitations in other fields appear. The total energy is conserved. The fields are the stage, the particles are the actors, and the stage is everywhere. Most of the time, we do not notice the fields because they are uniform. The electron field has the same ground state value here as it does on the other side of the galaxy. You cannot see it. You cannot feel it. It has no direct effect on your senses. What you notice are the excitations, particles, light, matter. Those are the things that interact with your body and produce sensations. The underlying fields are invisible, but they are the more fundamental thing. A particle is a temporary pattern. The field is permanent. Particles come and go. The field endures. The field concept also changes how you think about forces. In quantum field theory, forces are explained by the exchange of particles. The electromagnetic force, for example, is mediated by photons. When two electrons repel each other, the repulsion is not action at a distance. It is the result of photons being exchanged between them. The electrons are excitations of the electron field. The photons are excitations of the photon field. The interaction is a coupling between the two fields. One electron emits a photon, the other absorbs it. Momentum is transferred. The electrons move apart. The photon that mediates the force is virtual. It does not have to satisfy the usual relationship between energy and momentum that a real photon would. It can exist for a short time, do its job, and disappear. The uncertainty principle allows this. Over short enough timescales, energy does not have to be precisely conserved. Virtual particles exploit that loophole. The strong force, which holds quarks together inside protons and neutrons, is mediated by gluons. Gluons are excitations of the gluon field. Quarks are excitations of quark fields. The weak force, responsible for radioactive decay, is mediated by W and Z bosons. Even gravity, in the quantum picture, should be mediated by a particle called the graviton, an excitation of the gravitational field. Gravitons have never been detected. Gravity is so weak compared to the other forces that individual gravitons are far beyond our ability to measure, but the structure of the theory suggests they exist. Every interaction, every force, every process in the universe is fields interacting. Particles are the language we use to describe excitations of those fields when the excitations are localized and carry definite energy and momentum. But at the deepest level, reality is fields. Space is not a container with particles moving through it. Space is a superposition of fields, each one filling the void, each one capable of being excited into patterns we call particles. This picture is so different from our intuitive sense of reality that it takes effort to internalize. We see objects, solid, separate, distinct, a table, a chair, a person. We think of them as made of atoms, and atoms as made of particles, and particles as little balls, but they are not. The table is a pattern of excitations in the electron field and the quark fields, held together by excitations in the photon field and the gluon field. The atoms are not tiny solar systems. They are overlapping probability clouds, regions where the fields have high amplitude, where you are likely to find an excitation if you measure. The solidity you feel when you touch the table is the electromagnetic repulsion between the electron clouds in your hand and the electron clouds in the table. Fields pushing against fields, no contact in the classical sense. Just forces mediated by particle exchange happening on scales too small and too fast to perceive. And beneath all of it, filling every gap, every space between the excitations, is the vacuum, the ground state of the fields, not empty, not inert, but seething, in a quantum sense, with potential. The vacuum is the lowest energy state, but it is not static, it fluctuates. Pairs of virtual particles appear and disappear, borrowing energy from the uncertainty principle and paying it back before anyone can measure the violation. The fluctuations are tiny, they average to zero, but they are there. They affect atoms, shift energy levels, create forces. The vacuum is alive. So when you look at the night sky, at the vast stretches of darkness between the stars, you are not looking at nothingness. You are looking at space filled with every field that exists. Most of them are in their ground state. No excitations, no particles, but the fields are there, waiting. A photon passing through that darkness is an excitation in the photon field propagating through a region where the field is otherwise quiet. A cosmic ray, a proton accelerated to near light speed by some distant supernova or black hole, is an excitation in the quark and gluon fields screaming through the vacuum at a speed so close to the speed of light that time nearly stops for it. And the vacuum itself, the thing we call empty space, is the canvas. It is the background hum of the universe. The fields in their lowest state, buzzing with zero-point energy, fluctuating in ways too small to detect directly, but large enough to have measurable consequences. The cosmos is not made of things sitting in a void, it is made of fields. Particles are what we see when the fields ripple. The void is a myth. There is no void. There is only the field. This is what quantum field theory tells us, not as speculation, not as metaphor, as the best description we have of what the universe is actually made of, tested to absurd precision, confirmed in particle colliders, in atomic clocks, in the structure of matter, in the behavior of light. The fields are real. They are not a mathematical convenience. They are the substance of reality, and the vacuum, the supposed emptiness, is stranger than anyone thought. It is not the absence of everything, it is the presence of every field doing as little as possible. And as it turns out, even doing as little as possible is not the same as doing nothing. The vacuum has structure. It has energy. It can be bent, stretched, excited, and under the right conditions, it can even create particles out of nothing, or what looks like nothing. Because in quantum field theory, there is no such thing as nothing. There is only the ground state of the fields, and the ground state is never truly still. The vacuum is not empty. That is the simplest way to say it, and it is also the most uncomfortable. Empty space, the void between galaxies, the gap between atoms, the darkness you imagine when you picture nothingness, is not nothing. It is something, something active, something churning with energy, something that under the right conditions can produce particles where no particles existed a moment before. Not because energy is being created from nowhere, energy is conserved, but because the ground state of the quantum fields, the state we call the vacuum, has structure, and that structure is strange enough that calling it empty is not just wrong, it is the opposite of the truth. The trouble started with Werner Heisenberg. In 1927, the same year electrons were proven to behave like waves, Heisenberg discovered a fundamental limit to what could be known about a quantum system. He was working through the mathematics of quantum mechanics and realized that certain pairs of properties could not be measured precisely at the same time. The more accurately you measured one, the less accurately you could measure the other. The classic example is position and momentum. If you know exactly where a particle is, you cannot know how fast it is moving. If you know its momentum precisely, its position becomes a blur. The relationship is strict. The product of the uncertainties in position and momentum must be at least as large as Planck's constant divided by 4 pi. That is not a statement about measurement techniques. It is not about the clumsiness of our instruments. It is a statement about reality. The particle does not have a precise position and a precise momentum at the same time, not because we cannot measure both, because both do not exist simultaneously. The uncertainty principle applies to other pairs of quantities too, energy and time, for instance. The longer you wait to measure the energy of a system, the more precisely you can determine it. But if you measure the energy over a very short time interval, the uncertainty in the energy becomes large. The product of the uncertainty in energy and the uncertainty in time is bounded by Planck's constant. For a time interval of 1 second, the energy uncertainty is tiny, far too small to matter. But for a time interval of a trillionth of a second, the energy uncertainty becomes significant, and for time intervals near the Planck time, 10 to the minus 43 seconds, the energy uncertainty is enormous. What does that mean for empty space? If you look at a region of vacuum over a long time, the energy is well defined. It is the ground state energy of the fields, the lowest possible energy. But if you look at that same region over an extremely short time, the energy is not well defined. It fluctuates. It can be higher or lower than the average, and the fluctuation can be large as long as it does not last long. The uncertainty principle allows this. Borrow a large amount of energy for a short time, and you have not violated anything. Energy is conserved on average. Over long enough timescales, the fluctuations cancel out. But at any given instant, the vacuum is not sitting still. It is fluctuating wildly. What form do those fluctuations take? In quantum field theory, a fluctuation in energy corresponds to the creation of particle-antiparticle pairs, an excitation in the electron field and an excitation in the positron field, for instance. The two excitations appear together, exist for a brief moment, and then annihilate, returning the fields to their ground state. The time they exist is limited by the uncertainty principle. The larger the energy borrowed, the shorter the time allowed. For a pair of particles with a combined mass energy of 1 electron volt, the maximum lifetime is something like 10 to the minus 15 seconds. For heavier particles, the time is shorter. A proton-antiproton pair can only exist for about 10 to the minus 24 seconds before the energy debt has to be repaid. These short-lived excitations are called virtual particles. The name is unfortunate because it makes them sound less real than they are. Virtual particles are not imaginary. They are excitations of quantum fields that do not last long enough to be observed as free particles. You cannot catch one and put it in a jar. You cannot point a detector at it and say, "There it is." It lives and dies before any measurement can be completed, but it has effects. It interacts with other fields, it contributes to forces, and in some cases, its existence can be inferred from those effects with extraordinary precision. The vacuum in this picture is not a calm sea. It is a roiling froth of virtual particles constantly appearing and disappearing. At every point in space, at every instant, pairs of particles are blinking into existence and annihilating. Electrons and positrons, quarks and antiquarks, photons, gluons. Every type of particle allowed by the quantum fields. The denser the foam, the shorter the timescales you look at. Zoom in far enough, and space stops looking smooth. It becomes grainy, chaotic, impossible to pin down. John Wheeler, the physicist who gave black holes their name, called this picture quantum foam. At scales near the Planck length, 10 to the minus 35 meters, space-time itself is expected to become foamy, fluctuating not just in field values but in its very geometry. Space and time stop being continuous and start looking like a turbulent froth. Wheeler coined the term in 1955, long before there was any hope of testing it. He was extrapolating quantum mechanics down to the smallest possible scales and asking what the universe would look like there. The answer was foam. Most of the time we do not notice any of this. The virtual particles appear and disappear too quickly. The energy fluctuations average to zero. The vacuum looks empty because the fluctuations are happening on time scales and distance scales far below what our senses or even our instruments can resolve. But the fluctuations are there and they have consequences. Atoms are affected by them, forces are affected by them, the vacuum itself is affected by them, and in at least one case, the fluctuations produce a measurable force between objects that have no business exerting a force on each other. In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory. He was thinking about the forces between colloidal particles, tiny particles suspended in a liquid. The van der Waals force, a weak attraction that arises from quantum effects, was known to act between molecules. Casimir wanted to understand the force at larger distances. He realized that if you placed two perfectly conducting metal plates very close together in a vacuum, the quantum fluctuations of the electromagnetic field between the plates would be restricted. Only certain wavelengths of virtual photons could fit in the gap. Wavelengths longer than twice the separation distance would not fit. Outside the plates, all wavelengths were allowed. The result was that there would be more vacuum fluctuations outside the plates than inside. The imbalance would create a net force pushing the plates together. The force was tiny. For two plates separated by 1 micrometer, about the width of a bacterial cell, the force per square meter was less than 1/1000th of a Newton. But it was real, and it depended only on the distance between the plates and fundamental constants. No charge, no mass, no external fields. Just the vacuum and the restriction of its fluctuations. Casimir published the prediction in 1948. It took a decade for anyone to measure it. In 1958, a physicist named Marcus Sparnay performed the first experiments. His results were consistent with Casimir's prediction, though the uncertainties were large. Better experiments followed. By the 1990s, the Casimir force had been measured to within a few percent of the theoretical value. It was real. The vacuum had energy. And that energy could push. The Casimir effect is one of the cleanest pieces of evidence that the quantum vacuum is not nothing. You take two metal plates, you put them in a vacuum chamber, you pump out all the air. There are no particles between the plates, no light, no atoms, nothing you could point to and call matter. And yet the plates are pushed together by something. That something is the difference in vacuum energy inside and outside the gap. Virtual photons that cannot exist between the plates but can exist outside them. The force is a direct consequence of the fact that the ground state of the electromagnetic field has structure. The vacuum is not featureless. It responds to boundaries. It can be shaped, restricted, manipulated, and when you manipulate it, you feel a force. The energy density of the vacuum is harder to talk about because the theoretical prediction is absurd. If you take quantum field theory seriously and try to calculate the energy of the vacuum, you have to add up the zero-point energy of every mode of every field. Each mode contributes half of Planck's constant times its frequency. High-frequency modes contribute more. And there are infinitely many modes, one for each possible wavelength, all the way down to arbitrarily small distances. Add them all up and the total is infinite. Physicists deal with this by introducing a cutoff. They assume that quantum field theory stops working at very short distances, perhaps near the Planck length, and they only count modes with wavelengths longer than the cutoff. Even with the cutoff, the result is enormous. If you use the Planck length as the cutoff, the vacuum energy density comes out to something like 10 to the 113 joules per cubic meter. That is not a typo. 10 to the 113. For comparison, the energy density of matter in the universe, including all the stars, all the galaxies, all the dark matter, is about 10 to the minus 10 joules per cubic meter. The vacuum energy, if the naive calculation is right, is 10 to the 123 times larger than the energy density of everything else combined. That energy should dominate the universe. It should curve space-time so violently that galaxies could not form, stars could not form, atoms could not form. The universe should either have collapsed immediately after the Big Bang or expanded so fast that nothing could ever clump together. Obviously, that did not happen. The universe exists. Galaxies exist. You exist. So something is wrong with the calculation. Either quantum field theory breaks down at high energies in a way we do not understand, or there is some mechanism that cancels almost all of the vacuum energy, leaving only a tiny residual. How tiny? Observations of the expansion of the universe, particularly the acceleration driven by dark energy, suggest that the actual energy density of the vacuum is about 10 to the minus 9 joules per cubic meter. That is small, very small, but it is not zero. Dark energy, the mysterious force accelerating the expansion of the cosmos, is consistent with a cosmological constant, a term in Einstein's equations that acts like an energy density of empty space. The mismatch between the predicted vacuum energy and the observed dark energy density is about 120 orders of magnitude. That is the biggest discrepancy between theory and experiment in the history of physics. It is called the cosmological constant problem, or sometimes the vacuum catastrophe. Nobody knows how to solve it. There are proposals. Maybe there is a symmetry that cancels most of the contributions. Maybe the vacuum energy is screened by some unknown field. Maybe quantum gravity changes the calculation at small scales in a way that makes the infinity go away. None of these ideas have worked. The problem remains open. The vacuum is doing something, but what it is doing and why it is doing it so gently are mysteries. Despite the theoretical confusion, the vacuum energy is real. We see its effects. The Casimir force is one. The Lamb shift, the tiny change in the energy levels of hydrogen caused by virtual photons, is another. Precision measurements of the electron's magnetic moment show deviations from the simple Dirac equation that can only be explained by including the effects of virtual particles. Quantum electrodynamics, the theory that describes how electrons and photons interact, predicts these effects to absurd accuracy. The agreement between theory and experiment is better than 1 part in 10 billion. The virtual particles are not a convenient fiction. They are part of the calculation, and the calculation works. So what is actually happening? The language of particles popping into and out of existence is useful, but it is also misleading. Virtual particles are not little balls blinking on and off like Christmas lights. They are a way of talking about the fact that quantum fields fluctuate. The fluctuations are encoded in the mathematics of the theory. When you calculate the probability that an electron at point A will scatter to point B, the calculation involves summing over all possible intermediate processes. Some of those processes include the emission and reabsorption of photons. Some include the creation of electron-positron pairs. The sum includes everything allowed by the fields. The virtual particles are terms in that sum. They represent possible intermediate states. You never see them directly. You see their cumulative effect. The vacuum, then, is not a static background. It is the sum of all the quantum fluctuations that can happen within the constraints of the uncertainty principle. At any given moment, the fields are jittering. Tiny excitations appear, live for a fraction of a second, and disappear. Averaged over time, the excitations cancel. The net energy is the ground state energy, but the cancellation is statistical. At short timescales, the fluctuations dominate. The vacuum is a sea of temporary particles, ghosts that exist only long enough to interact with the real particles passing through. And sometimes, under the right conditions, the vacuum can produce real particles, not virtual ones. Real, observable, permanent particles. This happens near black holes. Stephen Hawking showed in 1974 that the intense gravitational field near a black hole's event horizon can split a virtual particle pair in such a way that one particle falls into the black hole and the other escapes. The escaping particle is real. It carries energy away from the black hole. From the outside, it looks like the black hole is radiating. Hawking radiation. The energy comes from the black hole's mass. The black hole shrinks. Eventually, over timescales vastly longer than the current age of the universe, the black hole evaporates completely. All of its mass is converted into radiation, and the radiation started as virtual particles in the vacuum near the horizon. The same thing can happen in an accelerating reference frame. If you accelerate through empty space, you will see a thermal bath of particles, a glow, even though an observer at rest in that space sees nothing. This is the Unruh effect, predicted in 1976 by William Unruh. The acceleration changes what counts as the vacuum. What looks like empty space to one observer looks like a warm gas of particles to an accelerating observer. The vacuum is not absolute. It depends on your state of motion. These effects are small. Hawking radiation from stellar mass black holes is far too faint to detect. The Unruh effect for any achievable acceleration is negligible, but they are consequences of the same underlying physics. The vacuum is not nothing. It is the lowest energy state of the fields, and that state is observer-dependent, context-dependent, and full of structure. Particles can emerge from it under the right conditions, not because energy is being created from nothing, but because what counts as a particle depends on how the fields are arranged. In curved spacetime, near a horizon, or in an accelerating frame, the distinction between vacuum and particles becomes ambiguous. The fields are still there, the excitations are real, but the line between ground state and excited state shifts. The foam picture extends all the way down to the Planck scale. At distances of 10 to the minus 35 meters, quantum fluctuations in the gravitational field become as large as the field itself. Spacetime stops being a smooth backdrop and becomes a seething, fluctuating structure. Distances and durations lose their meaning. The geometry of space itself fluctuates. Wormholes, tiny tunnels connecting distant regions of space, might form and collapse in fractions of a Planck time. The entire structure of space-time at the smallest scales might be radically different from the smooth continuum we see at large scales. This is speculative. No experiment has probed the Planck scale. No theory of quantum gravity has been confirmed. But the logic of quantum mechanics applied to spacetime suggests that the foam should be there, and if it is, then space and time themselves are emergent properties, averages over a chaotic substrate that looks nothing like the universe we experience. The implications are unsettling. If the vacuum is not empty, if space itself is a dynamic, fluctuating thing, then the solid, stable world we perceive is built on top of a foundation that is anything but solid or stable. The atoms in your body are sitting in a sea of virtual particles. The photons carrying this text from the screen to your eyes are propagating through a vacuum that is constantly producing and annihilating other photons, electrons, quarks, every particle in the standard model. The forces holding you together, the electromagnetic repulsion that keeps your atoms from collapsing, are mediated by virtual photons flickering in and out of existence faster than time can measure. Everything you touch, everything you see, everything you are, is a pattern imposed on a churning quantum foam that never stops moving. The cosmological constant problem looms over all of this. The vacuum has energy. We know that because dark energy is accelerating the expansion of the universe, but the amount of energy is incomprehensibly smaller than what quantum field theory predicts. If the prediction were right, the universe would have torn itself apart before the first atoms formed. If the prediction were completely wrong, if the vacuum energy were exactly zero, we would need an explanation for why such a perfect cancellation occurred. Instead, we have a tiny non-zero value. Not random, not predicted, just measured, and nobody knows why. Some physicists think the cosmological constant problem is a clue that quantum field theory is incomplete. Maybe there is a deeper layer of physics, something that cuts off the high-energy modes in a natural way and leaves a small residual vacuum energy. Maybe string theory, which replaces particles with tiny vibrating strings and requires extra dimensions of space, provides that cutoff. Maybe loop quantum gravity, which treats spacetime itself as made of discrete chunks, changes the calculation. Both approaches are speculative. Neither has made a confirmed prediction. The problem remains unsolved. Others think the vacuum energy might not be constant. Maybe it changes over time, evolving as the universe expands. Some models propose a field, similar to the Higgs field, that adjusts the effective vacuum energy. These are called quintessence models. They can fit the data, but they require fine-tuning. You have to pick the properties of the field very carefully to get the right energy density today. And fine-tuning is usually a sign that something is missing. Nature does not seem to require delicate adjustments. The fundamental constants are what they are, and the universe works. If a theory requires you to dial in numbers to 17 decimal places to match observations, you are probably not looking at the right theory. And then there is the anthropic explanation. Maybe the vacuum energy is not determined by any underlying law. Maybe it is random, different in different regions of a vast multiverse. In regions where the vacuum energy is too large, galaxies do not form, and there is no one to ask the question. In regions where it is too small, same result. We live in a region where the vacuum energy happens to be just right, because those are the only regions that produce observers. This explanation is unsatisfying to many physicists. It gives up on finding a deeper reason, but it might be right. The universe does not owe us a reason we find satisfying. What is clear is that the vacuum is not a passive stage. It is an active participant in every physical process. The fields that fill space are always there, always fluctuating, always ready to interact. The ground state is not the absence of fields. It is the state where the fields have minimum energy, and minimum does not mean zero. It means the lowest value allowed by quantum mechanics. The uncertainty principle forbids true stillness. Everything vibrates, even the vacuum. This brings us to the edge of the next question. If energy is fundamentally tied to the vibrations of fields, if particles are excitations and the vacuum is never still, then what is energy really? Not the classical picture of a smooth flowing substance, not even just the quantized packets Planck found. Energy is something deeper. It is a property of how quantum fields oscillate. And those oscillations have a frequency, a rhythm, a rate. Planck's constant sets the conversion between frequency and energy. E equals h times nu. The faster the field oscillates, the more energy each quantum carries. At the high end, at frequencies near 10 to the 19th cycles per second, the energy scale is enormous. At those frequencies, the quantum nature of energy stops being a subtle correction and becomes the entire story. The vibrations are the energy is the vibrations, and the universe runs on a clock that ticks faster than anything you can imagine. That is where the story goes next. Not to particles, not to fields, but to the vibrations themselves, the pulse beneath everything, the rhythm that has been running since the beginning and will keep running until the end, 10 to the 19th vibrations per second. That is the heartbeat of reality. And once you hear it, you cannot unhear it. Energy is not a thing. That sentence should feel wrong. Everything in your experience tells you that energy is real. You feel it when you get out of bed in the morning, or when you don't. You see it in the motion of a car, the glow of a light bulb, the heat rising from pavement on a summer afternoon. Energy is the reason your phone works, the reason your body works, the reason the sun has been burning for 4.5 billion years. Energy is everywhere. Energy is fundamental. Energy is, by every measure that matters, as real as anything gets. And yet energy is not a thing. It is not made of substance. It is not a particle, not a wave, not a field, not even an object in any meaningful sense. Energy is a number, a property, a way of keeping score when quantum fields vibrate. And the vibrations, those infinitesimal oscillations rippling through the fabric of space at rates so high that human language barely has room for the numbers, those vibrations are all there is. Everything else is what happens when you add them up. This is where the whole story has been heading. Planck found that energy was quantized. Einstein found that light came in packets. Dirac and the others found that particles were excitations of fields. The vacuum turned out to be a seething foam of virtual particles popping in and out of existence. Each step peeled back another layer. Each discovery made the universe seem less solid and more abstract, until we arrive here, at the edge of what quantum field theory actually says about the nature of reality. And what it says is this: matter is not made of particles, matter is made of patterns. Patterns in fields, and those patterns are vibrations, oscillations at specific frequencies with specific amplitudes governed by equations that relate frequency to energy in a way so precise that we can measure it to 12 decimal places. The formula is simple. Energy equals Planck's constant times frequency, E equals h times nu. The faster a field vibrates, the more energy it carries. That is not a metaphor, that is the mechanism. The vibrations are the energy is the vibrations, and everything you have ever seen, touched, or thought about is the result of those vibrations interacting in ways that produce the illusion of substance. Start with the simplest case, a photon, a quantum of light. We have already established that the photon is not a tiny ball flying through space. It is an excitation of the electromagnetic field. When you say a photon has energy, what you mean is that the electromagnetic field at that location is oscillating. The frequency of the oscillation determines the energy. Visible light oscillates at around 500 trillion cycles per second, 5 times 10 to the 14th hertz. Multiply that by Planck's constant, 6.6 times 10 to the minus 34 joule seconds, and you get the energy of a single photon of green light, about 4 times 10 to the minus 19th joules. That is a tiny amount of energy. A joule is the energy needed to lift a small apple 1 meter against gravity. A photon carries a trillionth of that. But the photon is not carrying energy the way a truck carries cargo. The energy is not inside the photon. The energy is the photon. The photon is what you call the oscillation when it is localized, when it behaves in a way that looks particle-like in an experiment. The oscillation is the fundamental thing. The particle is the label. Now go to an electron. Same story, different field. The electron is an excitation of the electron field. The field exists everywhere. At every point in space, the electron field has a value. Most of the time, most places, the value is at its minimum, the ground state. No excitations, no particles. But when the field is excited, when it develops a ripple, a localized oscillation, we call that ripple an electron. The electron has mass. Photons do not. Mass is a form of energy tied to the way the field interacts with the Higgs field, but that is a separate story. The point is that the electron, like the photon, is not a thing, it is a pattern, a wave packet, a region where the field amplitude is high, oscillating at a frequency determined by the electron's energy. And the electron's energy includes its rest mass, converted via Einstein's famous equation E equals mc squared, plus any kinetic energy from motion, plus any potential energy from its position in a force field. All of that together determines how the electron field is vibrating at that location. The relationship between energy and frequency is not optional. It is built into the structure of quantum mechanics. When you solve the Schrödinger equation for a free particle, the solutions are waves, plane waves to be specific. Waves with a definite frequency, and the energy of the particle is Planck's constant times that frequency. The equation does not care what kind of particle you are talking about. Photon, electron, quark, neutrino. The relationship is the same. Frequency and energy are locked together. You cannot have one without the other. High frequency means high energy. Low frequency means low energy. The proportionality constant is Planck's constant, the same number that showed up in the blackbody spectrum, the photoelectric effect, the uncertainty principle. It sets the scale for quantum mechanics. It tells you how much energy corresponds to a given oscillation rate, and it appears in every equation that describes how quantum fields behave. Different types of fields vibrate in different ways. The photon field, the electromagnetic field, is a vector field. It has a direction at each point as well as a magnitude. The oscillations are transverse, perpendicular to the direction of motion. That is why light is a transverse wave. The electron field is a spinor field. It has internal structure, quantum spin, that makes it behave differently from a simple scalar field. The oscillations of the electron field carry half-integer spin. That is why electrons are fermions, particles that obey the Pauli exclusion principle. Two electrons cannot be in the same quantum state at the same time. The gluon field, which mediates the strong force, is even more complicated. Gluons carry color charge and interact with each other, something photons do not do. The oscillations of the gluon field are non-linear, which is why the strong force gets stronger at long distances and weaker at short distances, the opposite of what intuition suggests. Each field has its own properties, its own symmetries, its own dynamics, but all of them vibrate. And the energy they carry is determined by the frequency of the vibration. What does it mean for a field to vibrate at a specific frequency? In classical physics, a vibration is a repetitive motion. A pendulum swings back and forth. A guitar string oscillates up and down. The motion repeats with a period, the time it takes to complete one cycle. The frequency is the number of cycles per second. In quantum field theory, the field is not a physical object moving through space. It is a mathematical function that assigns a value to every point in space and time. When the field vibrates, the value at each point oscillates. It goes up and down or rotates in some internal space, depending on the type of field. The oscillation has a frequency, and that frequency, multiplied by Planck's constant, gives the energy per quantum. If the field is oscillating slowly, the energy per quantum is low. If it is oscillating fast, the energy per quantum is high. The field itself is always there. The vibrations are transient. They come and go. They propagate through the field, creating patterns that we interpret as particles. The speed of the vibrations matters a lot. The frequency range covered by the electromagnetic field, from radio waves to gamma rays, spans more than 20 orders of magnitude. Radio waves oscillate at a few kilohertz to a few gigahertz, thousands to billions of cycles per second. Visible light oscillates at hundreds of terahertz, trillions of cycles per second. X-rays oscillate at exahertz 10 to the 18th hertz. Gamma rays from cosmic sources can reach 10 to the 24th hertz or higher. Each photon at those frequencies carries energy in the mega-electron-volt range, enough to ionize atoms, break chemical bonds, and shred DNA. The oscillation rate determines the energy. The energy determines what the photon can do. A radio photon cannot knock an electron out of an atom. It does not have enough energy. A gamma-ray photon can not only knock out an electron, it can create particle-antiparticle pairs from the vacuum if it collides with another high-energy photon. The frequency is not a detail, it is the defining feature. For matter particles, the frequencies are even higher. An electron at rest, with no kinetic energy, has a rest mass energy of about 511,000 electron volts. Plug that into E equals h nu and solve for frequency. You get about 1.2 times 10 to the 20th hertz, 120 quintillion cycles per second. That is the frequency associated with the electron's rest mass, the intrinsic vibration of the electron field when it is excited in the simplest possible way. If the electron is moving, the frequency increases. Faster motion means higher energy, means higher frequency. A proton, nearly 2,000 times heavier than an electron, has a rest mass energy of about 938 million electron volts. The corresponding frequency is about 2 times 10 to the 23rd hertz, 200,000 billion cycles per second. That is the vibration rate of the quark and gluon fields inside a proton, averaged over the complicated mess of interactions that hold the thing together. The proton is not a simple particle. It is a bound state of 3 quarks swimming in a sea of virtual quarks and gluons, all interacting through the strong force. The total energy of the system corresponds to a characteristic frequency, and that frequency is absurdly high. At the high end of the energy scale, the frequencies become almost unimaginable. The Planck energy, the energy scale where quantum mechanics and gravity are expected to merge, is about 1.2 times 10 to the 19 giga-electron volts, 10 billion electron volts. The corresponding frequency is about 3 times 10 to the 43 hertz. That is 10 to the 19th vibrations per second raised to the power of 10 to the 24. The number is so large that writing it out in full would take more digits than there are atoms in your body. At that frequency, the oscillations of the quantum fields are so violent that space-time itself breaks down. The distinction between space and time blurs, the geometry fluctuates. Cause and effect stop making sense. This is the Planck scale, the edge of known physics, the boundary beyond which all our current theories fail, and it is defined by a frequency, a vibration rate, the fastest meaningful oscillation the universe allows. Now here is the part that bends your brain. The vibrations are not happening in some medium. There is no ether, there is no substance that the fields are made of. The field is the medium. The field is the thing that vibrates, and the field is not made of anything else. It is fundamental. When you ask what the electromagnetic field is made of, the answer is nothing. It is a field. It exists. It has properties. It obeys equations. But it is not constructed out of smaller parts. The same is true for the electron field, the quark fields, all of them. They are the bottom layer, the substrate, the foundation of reality. And when they vibrate, we get particles. When the vibrations interact, we get forces. When the vibrations combine in stable patterns, we get atoms, molecules, cells, planets, galaxies, you. Everything that exists is a pattern of vibrations in quantum fields. The vibrations are not a metaphor for energy. They are what energy is. Different vibration modes give rise to different particles. This is not speculation. It is how quantum field theory works. The modes are the allowed patterns of oscillation. In a simple harmonic oscillator, a mass on a spring, the system can vibrate at a specific frequency determined by the mass and the stiffness of the spring. In a quantum field, the system can vibrate at any frequency, but each mode is quantized. The energy comes in integer multiples of Planck's constant times the frequency, 0 quanta, 1 quantum, 2 quanta, and so on. 0 quanta is the ground state, no particles. 1 quantum is a single particle. 2 quanta is 2 particles. The particles are identical because they are excitations of the same mode of the same field. An electron is a 1 quantum excitation of the electron field's lowest energy mode. A photon is a 1 quantum excitation of the electromagnetic field's mode corresponding to a specific frequency and polarization. A gluon is a 1 quantum excitation of one of the 8 color charge modes of the gluon field. Each particle type corresponds to a specific mode. Each mode has a characteristic frequency. Each frequency corresponds to an energy. The energy is the vibration. The forces also come from vibrations. This is where quantum field theory gets truly strange. In classical physics, a force is something that pushes or pulls. In quantum field theory, a force is the exchange of particles. The electromagnetic force between two electrons is mediated by photons, virtual photons. The electrons are excitations of the electron field. The photons are excitations of the photon field. The fields are coupled. When one electron field excitation changes, it can create an excitation in the photon field. The photon field excitation propagates. It reaches the other electron and gets absorbed, changing that electron's state. Momentum is transferred, the electrons move. We interpret this as a force. But at the fundamental level, it is fields vibrating, creating temporary excitations, those excitations propagating and interacting, and the result being a change in the state of the original excitations. The force is not a thing, it is a process, a pattern of vibrations exchanging energy and momentum through the coupling of fields. The strong force works the same way, except the particles being exchanged are gluons. The weak force is mediated by W and Z bosons. Gravity, if it fits into the quantum picture at all, would be mediated by gravitons. Every force is an interaction between fields. Every interaction is the creation, propagation, and absorption of field excitations. And every excitation is a vibration. The forces that hold you together, that keep your atoms from flying apart, that bind quarks into protons and protons into nuclei, are not invisible ropes or sticky glue. They are the result of quantum fields oscillating in coordinated patterns, exchanging energy in discrete packets at rates measured in trillions of cycles per second. The substance of the world, the solidity you feel when you touch a table or stand on the ground, is not substance at all. It is geometry, it is rhythm, it is vibration. Here is the truly unsettling part. If particles are vibrations and forces are vibrations and the vacuum is filled with fluctuating vibrations, then what is left that is not vibration? The answer is nothing. There is no solid core beneath the oscillations. There is no underlying stuff that does the vibrating. The vibrations are all there is. When you look at an atom, you are looking at a nucleus surrounded by an electron cloud. The nucleus is made of protons and neutrons. The protons and neutrons are made of quarks and gluons. The quarks are excitations of quark fields. The gluons are excitations of the gluon field. The electrons are excitations of the electron field. Every piece of the atom, every component, is a localized vibration of a quantum field. The fields overlap. They fill the same space. They interact. The interactions produce stable configurations, patterns that persist because the forces balance out, because the vibrations lock into phase, because the quantum numbers add up in the right way. The atom is not a collection of objects. It is a standing wave, a resonance, a mode of oscillation that happens to be stable under the laws of physics that govern this universe. You are made of atoms, trillions of them. Each atom is a pattern of vibrations. Each molecule is a more complex pattern. Vibrations coupled together through electromagnetic interactions mediated by more vibrations. Your cells, your tissues, your organs, your brain, all of it is vibrations layered on vibrations, patterns within patterns, held together by forces that are themselves nothing but the exchange of vibrational quanta between fields. The information in your DNA is encoded in the arrangement of molecules, which is encoded in the configuration of atoms, which is encoded in the state of quantum fields. When you think a thought, neurons in your brain fire. Electrical signals propagate along axons. Neurotransmitters cross synapses. All of that activity is electrons moving, molecules binding and unbinding, fields interacting, and at the bottom of every interaction is a vibration, an oscillation of a quantum field at a frequency corresponding to the energy being transferred. Your thoughts are vibrations. Your memories are vibrations. Your sense of self, the feeling that you are a coherent, continuous entity, is a pattern of vibrations so complex that it generates the illusion of a thing that persists through time. You are not a thing. You are a process, a temporary configuration of oscillating fields that has somehow become aware of itself. Energy, then, is not a substance that flows. It is a property of how fast the fields are vibrating. When energy is transferred from one system to another, what is really happening is that the oscillation pattern in one part of the field is changing and a new oscillation pattern is appearing somewhere else. The total energy is conserved because the total amplitude of the vibrations is conserved. The universe has a fixed amount of vibrational activity distributed across all the fields that exist. The distribution changes, patterns form and dissolve, excitations propagate. But the total, the sum over all the fields and all the modes, stays constant. Energy conservation is not a mysterious law handed down from on high. It is a consequence of the fact that the equations governing the fields do not change over time. Noether's theorem, proven by mathematician Emmy Noether in 1915, shows that every symmetry of the laws of physics corresponds to a conservation law. Time translation symmetry, the fact that the laws are the same today as they were yesterday, implies energy conservation. Energy is conserved because the universe does not care what time it is. The vibrations keep oscillating, the rules stay the same, and the total vibrational energy stays fixed. This is the true nature of energy, not a fluid, not a substance, not even a particle or a wave in the usual sense. Energy is the measure of how intensely quantum fields are vibrating. It is the currency of interaction because interactions are processes where vibrations in one field create or destroy vibrations in another. It is the fundamental quantity because it is directly tied to the most basic feature of quantum fields, their oscillation frequency. E equals h nu is not just a formula. It is the Rosetta Stone that translates between the abstract mathematics of quantum field theory and the physical phenomena we observe. Frequency is something you can measure. Energy is something you can calculate. The two are equivalent, interchangeable, different ways of describing the same thing. The number 10 to the 19th vibrations per second shows up because that is the scale where the quantum nature of energy becomes undeniable. At lower frequencies, the energy per quantum is so small that the quantization is invisible. A radio wave oscillating at 1 megahertz, 1 million cycles per second, has photons with energy around 4 times 10 to the minus 27 joules. You would need trillions of those photons to have enough energy to feel as heat. The radio wave looks continuous because you never interact with individual quanta. But at 10 to the 19th hertz, the energy per quantum is substantial. In the electron-volt scale, frequencies around 10 to the 19 hertz correspond to energies in the tens of kilo-electron-volts. That is X-ray territory. Each photon carries enough energy to knock inner shell electrons out of atoms. The quantization is not subtle. You can count individual photons with a detector. Each one makes a distinct click. The vibration is discrete. The energy is discrete. The connection is undeniable. And if you go even higher, up to the Planck frequency, 10 to the 43 hertz, the energy per quantum becomes comparable to the rest mass of a small black hole. A single quantum at that frequency would carry enough energy to warp spacetime so severely that it would collapse into a singularity. The vibration would be so intense that the field itself, the space-time geometry, could not support it. This is the energy scale where quantum mechanics and general relativity collide, where the smooth fabric of space-time predicted by Einstein's equations starts to look like a foaming, fluctuating mess. where the vibrations of the gravitational field become as important as the vibrations of matter fields, and where, most likely, the entire framework of quantum field theory as we currently understand it breaks down. We do not know what happens at the Planck scale. No experiment can reach it. No theory has successfully described it. But the vibrations are still there, faster than anything we can measure, more energetic than anything we can create, oscillating at the edge of what the universe allows. So here is the picture. The universe is made of fields. The fields fill all of space. They overlap. They interact. They obey equations that describe how they change. At every point, at every instant, the fields are oscillating. Most of the time, most places, the oscillations are minimal. The fields are in their ground state, vibrating just enough to satisfy the uncertainty principle. But where the oscillations are excited, where the amplitude is large, we see particles. Where the oscillations propagate, we see waves. Where the oscillations interact, we see forces. Everything that exists, everything that happens is vibrations. Fast vibrations, slow vibrations, complex superpositions of vibrations, patterns that persist, patterns that decay, patterns that combine into structures stable enough to last billions of years, atoms, stars, galaxies, all of it is rhythm. All of it is frequency. All of it is energy. Energy is not what you thought it was. It is not a thing you can hold or transfer or store in the way you imagined. It is a way of keeping track of how quantum fields are vibrating. When you say a system has energy, you mean its fields are oscillating at certain frequencies with certain amplitudes. When you say energy is transferred, you mean the pattern of oscillation is changing. When you say energy is conserved, you mean the total vibrational activity of all the fields is constant. The language is different, the concepts are different, but the math works. The predictions match experiments, and the picture that emerges is stark and strange and beautiful. The universe is not made of stuff. It is made of music. Not metaphorical music. Actual vibrations at definite frequencies, governed by precise rules. Music too fast to hear, too pervasive to see, too fundamental to ignore. You are listening to it right now. You are made of it. And every interaction, every thought, every moment of your existence is a note in a symphony that has been playing since the beginning of time. But even this picture, as clean and complete as it seems, is not the end. Because if particles are vibrations and vibrations are patterns and patterns are temporary, then what is the background against which those patterns appear? What is the silence between the notes? The fields are always there, but fields are mathematical structures. They are not made of anything tangible. They do not exist in space. They are space, or they define space, or they fill space in a way that makes the distinction between field and space meaningless. The deeper you go, the less solid anything becomes. The vibrations dissolve into equations. The equations dissolve into symmetries. The symmetries dissolve into abstract principles. And at the very bottom, beneath the oscillations, beneath the fields, beneath the mathematics, there is something that is not a thing, something that has no name, because naming it would be giving it properties it does not have. The ground state of everything, the silence, the stillness that allows the vibrations to be vibrations. That is where the story ends, or begins, depending on how you look at it. You are standing on nothing. That is not a metaphor. That is not poetic license. That is the most accurate statement I can make about your current physical situation, given what quantum field theory has spent the last century trying to tell us. The floor beneath your feet, the chair you are sitting in, the device you are holding, the neurons firing in your skull as you process these words, all of it, every particle, every force, Every interaction is not made of substance, it is made of patterns, vibrations in quantum fields that fill space, and those fields are not made of anything else. They are the bottom layer, the foundation. Except foundations are supposed to be solid, and these are not. They are mathematical structures that assign values to points in spacetime and evolve according to equations. When the values oscillate in the right way, we call it a particle. When the oscillations propagate, we call it a wave. When the oscillations interact, we call it a force. And when the oscillations combine into stable configurations that persist for billions of years, we call it matter. But none of it is substance in the way you think of substance. It is pattern all the way down, and beneath the patterns there is nothing. Not emptiness in the sense of a container waiting to be filled. Nothing in the sense that the question of what is there stops making sense. The fields are not in space. The fields are what space is made of, or what defines space, or what makes the concept of space coherent in the first place. The deeper you look, the less solid the distinction between something and nothing becomes, and that is where we are now, at the edge of the story, staring into the deep quiet beneath the vibrations. Let's collect the pieces. Energy is not a thing you can bottle or pour. It is a property of how quantum fields vibrate. Faster vibrations, higher frequency, more energy per quantum, that is the rule. E equals h times nu, Planck's constant times the frequency. The relationship is locked in, unbreakable. Every particle in the Standard Model, every photon, every electron, every quark, is an excitation of a corresponding field. The electron field fills the universe. Every cubic meter, every point from here to the edge of the observable cosmos. When that field develops a localized ripple, a standing wave pattern with the right energy and momentum, we detect an electron. The electron is not a tiny ball, it is the ripple, it is the pattern, it is the field doing something rather than nothing. And when the pattern dissipates, when the electron is annihilated by a positron or absorbed into a nucleus, the field returns to its ground state. The electron is gone. The field remains. The photon field is the electromagnetic field, quantized. Light is not a stream of tiny bullets. Light is a propagating disturbance in the photon field. When you see light, you are detecting excitations of that field arriving at your retina at a rate of trillions per second. Each excitation, each photon, carries energy determined by its frequency. The energy is not inside the photon like water inside a balloon. The energy is the photon. The photon is the oscillation. The oscillation is all there is. Take away the oscillation and there is no photon. There is only the field, silent, waiting, filling space with potential. The same applies to matter. Protons are not solid lumps. They are bound states of quark fields and gluon fields, held together by the strong force, which is itself just the exchange of gluons, which are excitations of the gluon field. The quarks are confined. They cannot exist as free particles outside the proton. They are trapped inside a region about 10 to the minus 15 meters across, vibrating, interacting, producing a net energy that we measure as the proton's rest mass, 938 million electron volts. Plug that into E equals h nu and you get a frequency, 2 times 10 to the 23 hertz. That is not the frequency of a single quark. Quarks do not have a single frequency. They are quantum objects in a complicated bound state. But the total energy of the system corresponds to a characteristic oscillation rate. And that rate is absurdly high, 200 sextillion vibrations per second. The proton is not sitting still. It is a storm of quarks and gluons, constantly emitting and reabsorbing virtual particles, fluctuating on timescales far too short to observe directly. We see the average, the net effect. a stable particle that lasts, as far as we know, forever. But zoom in, and the stability dissolves into chaos, vibrations on top of vibrations, patterns within patterns, all of it held together by forces that are themselves nothing but more vibrations. You are made of this. Your body contains roughly 7 times 10 to the 27 atoms. Each atom is a nucleus surrounded by an electron cloud. Each nucleus is protons and neutrons. Each proton and neutron is quarks and gluons. Each quark, each electron, each gluon is an excitation of a quantum field. There is no solid core. There is no underlying substance that the fields are made of. The fields are fundamental. They are not constructed from anything else. And when you ask what a field is, the only honest answer is that a field is a mathematical object that obeys certain equations and assigns values to points in spacetime. That is it. That is the definition. A field is not made of matter. It is not made of energy. It is not made of anything physical in the sense you are used to thinking about physical things. It is an abstract structure. And yet when that structure vibrates, you get electrons, you get photons, you get atoms, molecules, cells, brains, thoughts, consciousness, the entire hierarchy of complexity that leads from quantum fields to the thing reading this sentence. Now think about what that means for matter. Matter, in the classical picture, was the opposite of empty space. Matter was stuff. Solid, tangible, made of atoms that were themselves made of smaller particles that were hard, indivisible, real. Empty space was the absence of matter, the void, the nothing between the stuff. That picture is wrong, completely wrong. There is no stuff. There are only fields, and fields fill all of space. The electron field is not just near electrons, it is everywhere. The photon field is not just where light is shining, it is everywhere. Every field that exists, every field corresponding to every particle in the Standard Model, occupies the same space. They overlap, they coexist, and most of the time, most places, they are in their ground state. No excitations, no particles, but the fields are still there. The vacuum, the so-called empty space, is not the absence of fields. It is the presence of fields in their lowest energy configuration, and that configuration is not static. The ground state of a quantum field is not like a pond sitting perfectly still. It is more like a pond on a windy day, with tiny ripples constantly forming and disappearing. The uncertainty principle forbids true stillness. Energy and time cannot both be precisely defined. Over short timescales, energy can fluctuate. The vacuum fluctuates. Virtual particles, particle-antiparticle pairs, pop into existence, live for a fraction of a second, and annihilate. The fluctuations are real. They have measurable effects. The Casimir effect, the Lamb shift, the electron's anomalous magnetic moment. All of these phenomena are explained by the vacuum being active, filled with temporary excitations that exist only long enough to interact with real particles before disappearing. The vacuum is not nothing. It is a seething foam of quantum activity, happening on scales too small and too fast to observe directly, but large enough to affect every atom, every force, every interaction. So the distinction between matter and empty space collapses. Matter is regions where the fields are highly excited. Empty space is regions where the fields are in their ground state. But the fields are the same fields. They do not turn on and off. They do not appear and disappear. They are always there, filling space, defining space. The difference between a region with matter and a region without matter is just a difference in how the fields are vibrating. That is all. No boundary, no edge, no fundamental separation, just amplitude, just frequency, just pattern. This dissolves more than matter. It dissolves the entire scaffolding of concepts we use to think about the world. Solidity is an illusion. When you press your hand against a table, you are not touching solid matter. The electron clouds in your hand are repelling the electron clouds in the table through the electromagnetic force. The force is mediated by virtual photons, excitations of the photon field that exist for a tiny fraction of a second before being absorbed. The repulsion is the result of those photons transferring momentum. There is no contact. There is no surface. There are just fields interacting, vibrations exchanging energy, patterns pushing against patterns. The sensation of solidity is your brain's interpretation of billions of tiny electromagnetic interactions happening per second. The solidity is not in the table. It is in your nervous system. It is the story your neurons tell when certain signals arrive in a certain pattern. Persistence is an illusion. You think of yourself as a continuous entity, the same person you were yesterday, the same person you will be tomorrow. But the atoms in your body are constantly being replaced. The water you drink becomes part of your cells. The food you eat becomes part of your tissues. The carbon dioxide you exhale was part of your blood a moment ago. Every atom in your body will be replaced within a few years, some faster, some slower, but none of them permanent. And beneath the atoms, the particles themselves are not persistent. They are excitations of fields. The electron that was part of a molecule in your brain a second ago might have decayed into a photon and a neutrino if the conditions were right. Particles are not eternal. They are events. They are temporary. The persistence you feel is not the persistence of substance. It is the persistence of pattern. Your body maintains a certain configuration, a certain structure, a certain set of processes that run continuously, replacing parts while preserving the whole. You are not a thing. You are a pattern that renews itself. Separation is an illusion. You think of yourself as separate from the world around you. Your body ends at your skin. The air you breathe is outside you. The floor beneath you is a different object. But at the quantum level, there are no boundaries. The electron field in your body is the same field as the electron field in the air, in the floor, in the earth, in the sun, in the most distant galaxy. It is one field. When an electron in your body interacts with a photon, the interaction happens because the electron field and the photon field are coupled. The coupling exists everywhere. The fields are not separate. They are aspects of a single underlying structure. The universe is not made of separate objects interacting across space. It is made of fields filling space, and the interactions are processes internal to those fields. You are not separate from the universe. You are a localized pattern in the fields that make up the universe. The boundary between you and not you is a convenient fiction, useful for navigation, for survival, for communication, but not real in any fundamental sense. The fields do not recognize the boundary. They do not stop at your skin. They extend outward, inward, everywhere. The separation is a label, a way of organizing information, not a feature of reality. Which brings us to consciousness. This is where the story gets uncomfortable. Because if you are not a thing, if you are a pattern of vibrations in quantum fields, then what is the thing that is aware of being a pattern? What is the thing that is reading this sentence and understanding it? What is the observer? Quantum mechanics has spent a century dancing around this question without answering it. The measurement problem, the collapse of the wave function, the role of observation in determining outcomes, these are not solved problems. They are open wounds in the theory. The math works. The predictions match experiments, but the interpretation, the story we tell about what is actually happening, remains contested, fiercely contested. In the Copenhagen interpretation, the act of measurement causes the wave function to collapse. Before measurement, A particle does not have a definite position or momentum. It exists in a superposition of all possible states. Measure it, and the superposition collapses. You get a definite outcome. But what counts as a measurement? Does it require a conscious observer? Does the particle know it is being observed? Niels Bohr said the question was meaningless. The wave function is not a description of reality. It is a description of our knowledge. The collapse is not a physical process. It is an update to our information. But that feels like dodging the issue. If the wave function is just knowledge, then what is it knowledge about? What is the underlying reality that the wave function describes? In the many worlds interpretation, there is no collapse. The wave function never collapses. Every possible outcome happens. When you measure a particle's position, the universe splits into branches. In one branch you measure it here, in another branch you measure it there. Both outcomes are real. Both versions of you exist. Consciousness does not cause collapse because there is no collapse. There is only branching. This interpretation is mathematically clean. It takes the equation seriously and does not add extra postulates, but the price is high. You have to accept that there are infinitely many copies of you splitting off every time a quantum measurement happens anywhere in the universe. Most physicists find that unpalatable, not because it is wrong, because it is extravagant. The universe does not owe us simplicity. But infinitely many universes is a hard pill to swallow. In the pilot wave interpretation, particles have definite positions at all times. The wave function guides the particle, like a pilot wave. Measurement reveals the position that was always there. No collapse, no branching, just deterministic evolution. But the price here is non-locality. The pilot wave can instantaneously affect particles across arbitrary distances, faster than light, not in a way that lets you send signals, so it does not violate relativity in a practical sense, but it violates the spirit of relativity, the idea that local interactions are all that matter. The pilot wave connects everything. The universe is a single, interconnected system. No separation, no independence. Every particle is guided by a wave that depends on the configuration of every other particle. The universe is holistic, not modular. None of these interpretations mention consciousness as a requirement. The role of the observer is a question about what constitutes a measurement, not about whether minds are special. But some physicists, starting with Eugene Wigner in the 1960s, have argued that consciousness is necessary to collapse the wave function. Wigner's argument was that only a conscious observer can turn a superposition into a definite outcome. A particle interacting with a measuring device creates a superposition of device states. A device interacting with an environment creates a superposition of environment states. The chain continues until a conscious mind looks at the result. At that point, and only at that point, does the superposition collapse. Wigner later retracted this view. He decided it led to absurdities. But the idea persists. It is appealing to people who want consciousness to matter, who want minds to be more than just complicated arrangements of particles, who want there to be something special about awareness. The problem is, there is no evidence for it. No experiment has ever shown that consciousness affects quantum outcomes in a way that unconscious measurements do not. Particles interact with detectors. Detectors register outcomes. The outcomes are consistent with the predictions of quantum mechanics. No mind required. Decoherence, the process by which quantum superpositions are destroyed through interaction with the environment, happens constantly. Every photon scattered by an atom, every air molecule colliding with a dust particle, every interaction with a thermal bath of radiation, all of it causes decoherence. The superposition does not collapse into a single outcome. It spreads out into the environment, becoming entangled with so many degrees of freedom that the interference terms become unobservably small. The system behaves classically not because a mind looked at it, but because the environment looked at it. And the environment is always looking. So consciousness is not required by quantum mechanics. But consciousness is built by quantum mechanics. Your brain is made of atoms. Atoms are made of particles. Particles are excitations of quantum fields. The neurons firing in your head, the synapses transmitting signals, the molecular cascades that encode memory and thought, all of it is quantum field theory in action. You are not outside the system, you are part of it. An extraordinary complex part, a pattern of vibrations so intricate that it has become self-referential, but still part of the same substrate. Awareness is not a separate substance. It is not a ghost in the machine. It is what certain patterns of vibration do. When the pattern is complex enough, when the feedback loops are tight enough, when the information processing reaches a certain threshold, awareness emerges. We do not know the threshold, we do not know the mechanism, but we know it happens. You are proof. The fact that there is something it is like to be you, that there is an inner experience, a subjective feeling of being, is a phenomenon. It is a phenomenon produced by matter, by fields, by vibrations. And that means consciousness, whatever it is not separate from the physical world. It is the physical world looking at itself. The universe, then, is not made of separate things. It is one thing, a unified field, not in the sense of a single theory that explains all the forces, though physicists have been chasing that for decades. Unified in the sense that all the fields that exist are aspects of a single structure. Spacetime is a field. The gravitational field is the curvature of spacetime. The electromagnetic field sits on top of spacetime. The electron field sits on top of spacetime. The quark fields, the gluon field, the Higgs field, all of them sit on top of spacetime, all of them filling the same space, all of them interacting through couplings encoded in the equations. The fields are not separate. They are facets of one thing, one mathematical structure that obeys one set of rules. The Standard Model plus general relativity, not a complete picture, there are gaps. Quantum gravity is missing, dark matter is unexplained, dark energy is unexplained, but the structure we have is coherent, it works, and it describes a universe that is not fragmented into separate objects, but woven into a single tapestry of interacting fields. That is what the vibrations are. They are the threads of the tapestry. Different frequencies, different amplitudes, different patterns, but all part of one fabric. When the threads vibrate in one pattern, you get an electron. When they vibrate in another pattern, you get a photon. When they vibrate in an enormously complex pattern, you get a brain. When the brain vibrates in a certain way, you get a thought. And when that thought includes the realization that it is a vibration, that the thinker and the thought and the universe are all made of the same fundamental stuff, that nothing is solid and everything is process, you get something close to what mystics have been trying to describe for thousands of years. Except now we have the equations, we have the experiments, we have testable predictions that match reality to 12 decimal places. This is not mysticism, this is physics, and physics is telling us that the universe is a symphony, not a metaphor, a literal symphony. Vibrations at different frequencies, harmonizing, interfering, creating patterns that evolve over time. You are a chord in that symphony, a sequence of notes, a theme that plays for a few decades and then resolves back into silence. Not gone, not destroyed, just dissolved back into the field. The vibrations that made you do not disappear, they change form. The energy is conserved. The pattern disperses. The atoms that were part of your body will become part of something else. The fields that were excited in the shape of you will be excited in other shapes. The music continues. The symphony plays on. Now here is the hardest part, the part that takes everything we have built and asks you to let go of it. The vibrations are real, the fields are real, the equations are real in the sense that they describe what happens with astonishing accuracy. But what are the equations describing? What is the substrate? What is the thing that vibrates? We have said the fields are fundamental, that they are not made of anything else. But that is not an answer. That is a stopping point, a place where we run out of deeper explanations and say this is as far as we can go. The fields are, they exist, they have properties, they obey rules. But we do not know why they exist. We do not know why they obey the rules they obey. We do not know why the constants have the values they have. Planck's constant, the speed of light, the charge of the electron, the masses of the quarks. All of these are measured, not derived. They are inputs to the theory, not outputs, and nobody knows why the inputs are what they are. Some physicists think the constants are arbitrary. There is a vast landscape of possible universes, each with different constants, and we live in one where the constants happen to allow complexity, structure, life, consciousness, the anthropic principle. We are here because if the constants were different, we would not be here to ask the question. Other physicists think the constants are determined by some deeper principle we have not discovered yet. A theory of everything that explains why the universe is this way and not some other way. String theory, loop quantum gravity, causal set theory. A dozen other proposals, none of them confirmed, all of them speculative. The truth is, we do not know. We do not know why the universe exists. We do not know why it has the structure it has. We do not know why there is something rather than nothing. These are not physics questions anymore. They are philosophy, metaphysics, questions that sit at the boundary between what can be tested and what can only be contemplated. But here is what we do know. The something that exists is not made of substance. It is made of relationships, patterns, processes. The fields are defined by how they interact. An electron is an electron because of how the electron field couples to the photon field, the Higgs field, the weak force fields. Take away the couplings and the field loses its meaning. The particles are not objects with intrinsic properties. They are nodes in a web of interactions. The web is the reality. The nodes are labels we give to stable patterns in the web. And the web itself is not made of anything. It is structure, pure structure. Mathematics made manifest. Or maybe mathematics is the only way we have to talk about structure, and the structure is something deeper than mathematics, something we do not have words for, because words are built from concepts, and concepts are built from experience, and our experience is of a macroscopic world where objects seem solid and separate and real. We do not have the cognitive tools to think about a reality made of pure process. We try, we build models, we write equations, we do experiments, and the experiments confirm the models. But the models are maps, not the territory. The territory is something we can point to with math, but not picture. Not visualize, not hold in our minds the way we hold the image of a tree or a mountain. And beneath the structure, beneath the equations, beneath the fields, there is the deep quiet. The thing that has no name because it is not a thing. The ground state of the ground state, the silence from which the vibrations arise. You cannot measure it. You cannot interact with it. You cannot point to it and say, here it is. Because if you could interact with it, it would not be the ground. It would be another layer of structure. The deep quiet is not absence. It is not emptiness. It is the background against which presence becomes possible. It is the 0 point, the reference, the still center around which everything turns. In meditation traditions, this is what they are pointing at when they talk about the void, the emptiness, the ground of being. Not nothingness in the nihilistic sense, but the condition that allows somethingness, the substrate that is not itself a thing but makes things possible. Physics does not talk about this. Physics stops at the fields, but the fields themselves are structure, and structure requires something to structure. Or maybe structure is self-sufficient. Maybe the fields are all there is, and asking what they are made of is like asking what is north of the North Pole. A category error, a question that assumes there must be an answer when maybe there is not. What is certain is that the picture you started with is gone. The world is not made of objects sitting in a void. The world is a unified field of vibrating patterns, creating the illusion of substance, the illusion of separation, the illusion of time flowing and things changing and you being a distinct entity with a persistent identity. The illusions are not false in the sense that they do not exist. They exist, you experience them. They are real experiences, but they are not fundamental, they are emergent. They arise from the interactions of quantum fields in the same way that the wetness of water arises from the interactions of water molecules. Wetness is not a property of individual molecules. It is a property of many molecules interacting. Solidity is not a property of individual atoms. It is a property of many atoms interacting. You are not a property of individual particles. You are a property of trillions of particles interacting in a configuration that produces awareness. The particles are excitations of fields. The fields are aspects of one structure. The structure is pure process, and the process is all there is. So when you stand on the floor, you are not standing on something. You are standing on a pattern of vibrations that happens to be stable enough to support another pattern of vibrations. When you look at the sky, you are not looking at empty space. You are looking at the ground state of quantum fields, filled with potential, waiting for something to excite them into light, into matter, into form. And when you think a thought, you are not a thing having an experience. You are an experience arising from a pattern of vibrations so complex that it has become self-aware. The thinker is the thought. The observer is the observation. The universe is not something you are in. You are something the universe is doing. A temporary eddy in the flow, a local increase in complexity. A note in the symphony that plays once and never exactly the same way again. And then the vibrations slow. The pattern dissipates. The fields return to their ground state, not gone, not destroyed. Energy is conserved, but the configuration that was you is lost. The information is scattered. The atoms are recycled. The energy moves into other forms. The music continues. The symphony does not end. It just stops playing your theme. And what is left is the deep quiet, the background hum, the ground state that was always there, beneath the noise, beneath the vibrations, beneath the appearance of things, silent, still, waiting, not empty, not absent, just quiet, the silence from which all sound arises and to which all sound returns. You came from that silence. You are going back to it. And while you are here, while the pattern that is you is vibrating, you get to witness the extraordinary fact that the universe has arranged itself into a form capable of understanding that it is a universe. That understanding is not separate from the universe. It is the universe looking at itself, fields examining fields, vibrations aware of vibrations. And for a brief moment, in this tiny corner of space-time, the deep quiet woke up. It took form. It opened its eyes, and it saw itself. That is what you are. That is what this is. Reality dissolved down to its foundation. Not matter, not objects, not even particles and fields in the way you first imagined them. just process, just vibration, just pattern, and beneath it all, quiet, deep, impenetrable, infinite quiet, the ground of being, the silence from which everything comes and to which everything returns. You cannot reach it while you are vibrating. You cannot know it while you are a pattern, but it is there, it has always been there. And when the vibrations stop, when the pattern fades, when the music resolves, that is what is left. Not death, not absence, just the deep quiet of being, still, silent, whole, waiting for the next vibration to begin. You woke up this morning in a world made of things, solid things, objects with weight and edges and permanence, a floor beneath you, a sky above you, a body that feels continuous, stable, yours. That world, the one your senses built for you, the one evolution tuned you to navigate, is not wrong exactly. It is just not fundamental. It is a summary, a user interface. A cartoon drawn by your nervous system to help you survive long enough to have children who will also believe the cartoon is real. Underneath the interface, beneath the objects and the separations, and the sense that you are a thing standing in a world full of other things, there is only this. Fields, everywhere, filling space, overlapping, vibrating. The electron field is not near electrons, it is everywhere. The photon field is not where light is shining, it is everywhere. Every field that exists occupies the same space, the same points, the same infinite grid that we call the universe, and at every point, at every instant, those fields are doing something. Most of the time, they are doing as little as possible. The ground state, the lowest energy configuration, but even that is not stillness. The uncertainty principle forbids it. The vacuum is alive, fluctuating, churning with virtual particles that exist for fractions of a second before annihilating back into the field. And when the fields are excited, when they develop ripples, standing waves, localized oscillations, we see particles, we see light, we see matter, we see forces, we see the world. But there is no world in the sense you thought. There is no collection of separate objects interacting across space. There is one structure, one mathematical object evolving according to one set of rules. The fields are not things, they are relationships, patterns of correlation. When the electron field oscillates here, the photon field responds there. The coupling between them is the force. The interaction is the reality. The particles are labels, convenient fictions, ways of talking about localized excitations in a structure that is fundamentally non-local, fundamentally unified, fundamentally one. You are not separate from this. You are not an observer watching the universe from outside. You are a pattern in the fields. A configuration of vibrations so complex, so tightly integrated, so recursive in its self-reference, that it produces the sensation of being a distinct thing, a self, an observer.